October of the year 2025 marks a historic milestone in our cosmic observations, a moment unprecedented in recorded history. For the first time, two distinct celestial objects are hurtling toward the sun from entirely different origins, their paths intersecting our solar neighborhood in a manner that defies previous expectations. One of these visitors, confirmed as an interstellar wanderer, bears a chemical signature that challenges the long-held principles of stellar formation, suggesting a journey that began far beyond the familiar confines of our solar system. Meanwhile, the other, a comet designated Swan R2, has exhibited a sudden and dramatic increase in brightness, hinting at a composition unlike any comet from our own distant Oort cloud. These two objects are on a collision course with our star, their approaches so precisely timed that they are creating what can only be described as a celestial traffic jam. An event that, according to the laws of probability and orbital mechanics, should occur only once every several million years. Yet here they are, both scheduled to make their closest approach to the sun within a span of just 28 days. Ground-based observatories and space agencies worldwide are meticulously tracking their trajectories, employing advanced calculations to predict their paths with mechanical precision. What makes this scenario even more compelling is that the instruments observing these objects are detecting chemical anomalies that challenge decades of scientific understanding about cometary composition and behavior. These anomalies may point toward origins or processes that are entirely outside the realm of conventional science. But the intrigue deepens as both objects sink deeper into the sun's intense glare. During their most critical phases, when tidal forces, solar radiation, and magnetic interactions are at their peak, our telescopes will be rendered completely blind. This deliberate obscuration raises an unsettling question. What if this timing is no accident? What if there is some unseen force or influence that does not want us to observe what is happening? Join me as we delve into why October 25, 2025 might just turn our understanding of the universe on its head. A period that could redefine what we believe is possible about what lurks beyond our familiar cosmic horizon. Part 1. Two lights in the sky. Two strangers have arrived in our solar system, one slender and swift, glowing with an eerie, otherworldly green hue. The other sprawling and radiant, its tail stretching across degrees of the night sky. These visitors originated from vastly different regions of space, yet now they are converging on our sun in a cosmic choreography so precise that astronomers are double-checking their calculations. The first of these arrivals materialized on July 1st, 2025, observed through the digital eyes of the Atlas Survey telescope in Chile. It appeared as a faint pixel, a tiny point of light in the vastness of space where none should have been. Within hours, orbital mechanics revealed the startling reality. This object, designated 3I Atlas, was hurtling along a hyperbolic trajectory, unmistakably unbound from the sun's gravitational grip. It was an interstellar visitor, only the third confirmed of its kind, coming from the far reaches beyond our solar system's edge. Just a few months later, a second object emerged from the solar glare like a ghost materializing at dawn. This was Comet C-2025 R2, discovered in imagery from the Swan instrument aboard the Solar and Heliospheric Observatory, SOHO, on September 11, 2025. It was already bright enough to be seen with binoculars, its tail developing rapidly, earning praise from amateur astronomers as magnificent in its display. In the sterile, humming corridors of NASA's Jet Propulsion Laboratory, computers process a continuous stream of telemetry data, each packet revealing stories of brightening curves, spectral signatures, and orbital refinements measured with extraordinary precision, often to the tenth of an astronomical unit. These measurements help refine our models, Yet no amount of data can fully capture the awe of witnessing these objects hanging silently above us in the night sky. Step outside on a clear October evening far from the orange glow of city lights, and you might catch fleeting glimpses of both visitors. Through a modest telescope, 3-Eye Atlas appears as a faint green-tinted smudge, subtle but unmistakable to trained eyes. Meanwhile, Swan R2 dominates the western horizon after sunset, its luminous tail sweeping upward like a cosmic brushstroke against the darkening sky. The instruments that track these objects communicate in frequencies beyond the reach of human hearing, capturing photons that traveled millions of years across the void, whispering secrets from distant corners of the universe. The story they tell is one of complexity and mystery. Spectral signatures revealing unexpected chemical signatures, deviations from known cometary behavior, and trajectories that seem almost orchestrated. As they approach the sun, both objects are poised to give us a rare and extraordinary glimpse into the dynamics of the cosmos. If only we can observe them before the sun's glare blinds us. Its tail unfurls and sweeps upward like a cosmic brushstroke, an elegant streak of light painted across the darkening canvas of the night sky. The instruments peering into the depths of space speak in frequencies we are unable to hear directly, their signals echoing across the void with a precision that surpasses human perception. The steady staccato rhythm of CCD shutters captures photons, tiny packets of light that have traveled millions of years through the expanses of time and space to reach us. Meanwhile, spectrographs, delicate electronic whisperers, dissect this starlight, decomposing it into its fundamental elements and revealing the chemical fingerprints of these distant objects. Ground-based stations scattered across the globe relay their findings in streams of data that flow relentlessly like digital rivers coursing toward analysis centers. There, human minds struggle to interpret the vast arrays of information, trying to decipher what these machines are revealing about objects that seem to defy simple understanding. Yet amid this symphony of signals and data, space itself remains utterly silent. No air, no sound, nothing can traverse the vacuum that separates worlds. Instead, electromagnetic radiation serves as the bridge, carrying encoded information in waves of light that tell stories beyond our immediate grasp. These waves whisper hints that these objects are not quite what they outwardly seem to be. In this cosmic dance, the interstellar visitor known as 3-Eye Atlas moves with purposeful determination, its trajectory charted by something that appears to know exactly where it is headed. Its path will bring it closest to our sun on October 29th, 2025, at a distance of approximately 1.35 astronomical units, just inside Mars's orbit. For such an object originating from beyond our solar system, this represents an astonishingly close approach, one that stirs questions and unease among astronomers and observers alike. It's close enough to ignite a series of uncomfortable inquiries about the nature and origins of such visitors. Meanwhile, Swan R2 follows its own schedule. It reached perihelion on September 12, 2025, plummeting to within half an astronomical unit of the sun, an almost daring dive into the solar inferno before beginning its outward journey into the depths of space. Its closest approach to Earth, however, will come later on October 21st, when it passes within a mere 0.27 astronomical units, practically skimming the very edge of our atmosphere in cosmic terms. This proximity is enough to make astronomers feel as if the comet might touch down, sparking sleepless nights and long hours behind glowing screens as they track these objects from afar. What makes this scenario even more extraordinary is that these two objects hail from entirely different origins, one from the distant reaches of interstellar space, and the other from within our own cometary cloud, their convergence in our inner solar system, occurring within weeks of each other, hints at a cosmic coincidence so improbable that it challenges the bounds of statistical expectation. Yet here we are, witnesses to what might be the most remarkable coincidence in recorded astronomical history. Or perhaps something far more deliberate. The green hue of 3I Atlas has captured particular attention among scientists and enthusiasts. Spectroscopic analysis reveals the presence of diatomic carbon and cyanogen molecules, substances that fluoresce with a vivid green when excited by solar radiation. This natural phenomenon is common in comets as they approach the sun and begin to outgaze, releasing their icy mantle of volatile compounds. But the intensity and unwavering consistency of this coloration have raised eyebrows, especially among researchers who have dedicated their careers to understanding these wandering celestial bodies. It's as if this comet's chemical signature is speaking a language just a little bit different from what we expect. Swan R2, on the other hand, brings its own set of mysteries. Its rapid brightening as it emerges from solar conjunction suggests a composition that diverges from the typical makeup of comets originating from our own outer cloud. Its tail development unfolds in familiar patterns, the sweeping, streaming extension pointing away from the sun, yet with subtle differences that hint at a slightly foreign script, written in characters we do not yet fully understand. The scale of these objects matters profoundly in space. The contrast between our visitors could hardly be more stark. 3I Atlas appears as a slender needle of light, compact and purposeful. Its nucleus estimated to be only a few kilometers across, modest by the standards of known comets, but still enough to produce the activity we witness. These observations, gathered through a tapestry of advanced instruments and global collaboration, continue to deepen the enigma. Each measurement, each spectral signature adds a new layer to the unfolding story, one that challenges our assumptions about the nature and diversity of objects passing through our cosmic neighborhood. And yet, amid the complexity and the questions, the universe remains silent, revealing its secrets only through the language of light and radiation, mysterious, distant, and profoundly intriguing. In the vast canvas of the night sky, Swan R2 unfolds like a shimmering veil, its luminous glow stretching across the heavens. From Earth's vantage point, its coma and tail extend over degrees of arc, creating a breathtaking spectacle that hints at the dynamic activity within this celestial visitor. As we step into October of 2025, we find ourselves witnessing a remarkable event. Two cosmic travelers hurtling toward their closest approaches to our sun, their paths converging in a dance that may redefine our understanding of interstellar phenomena. One of these visitors, the interstellar wanderer designated as 3I Atlas, is set to be observed closely by our robotic explorers orbiting Mars. On October 3rd, the red planet's orbit will bring it within a mere 30 million kilometers of the approaching object. During this fleeting window, our carefully deployed spacecraft, equipped with high-resolution cameras and sensitive spectrometers, will turn their instruments toward this enigmatic visitor, collecting vital data. These observations might finally shed light on the questions that have been mounting with each passing measurement. What is the true nature of this object? Where did it come from? And what secrets does it carry? Yet despite these efforts, October presents an inevitable obstacle. As both visitors race closer to the sun, our view from Earth becomes increasingly obstructed by the bright glare of our star. Solar radiation will gradually dominate the sky, overwhelming the faint signals from these distant objects and rendering our ground-based telescopes blind during their most critical phases of approach. For weeks, possibly even months, we will be unable to track them, leaving us in uncertainty about their condition and progress. When, or if, they re-emerge from behind the sun's luminous veil, what stories will our instruments tell? Will these objects appear unchanged, bearing only the natural scars inflicted by their solar encounters? Or will they emerge transformed, perhaps bearing evidence of phenomena that challenge our current understanding of interstellar matter? This lingering question, simple in its phrasing yet profoundly complex in its implications, haunts these October nights. Is what we observe merely a comet, a fortress of unknown origin, or perhaps the silent reply to a message we never knew we sent into the cosmos? The universe has woven two mysteries into the fabric of our skies, and this fleeting window in October 25 might be our only chance to decipher them before they vanish into the dark expanses of space once more. But before we can interpret their stories, we must understand how we discovered them, and more critically, how they came to find us. The story of these cosmic visitors begins not with a sudden revelation or an awe-inspiring flash of insight, but with the slow, meticulous gathering of photons, tiny packets of light, captured by an array of silicon sensors spread across the globe. Each night, automated telescopes systematically sweep predetermined sections of the sky, their electronic eyes tirelessly recording images that are then compared, processed, and scrutinized by sophisticated algorithms. These digital sentinels are designed to detect anomalies, any sign that something out of the ordinary might be passing through our cosmic neighborhood. One such survey, the Atlas Project, was instrumental in uncovering the presence of 3 interstellar objects. It operates 4 telescopes strategically positioned across 2 continents, each equipped with wide-field cameras capable of monitoring vast stretches of the sky simultaneously. Every clear night, these observatories generate hundreds of gigabytes of data, capturing the positions and brightness of millions of stars with extraordinary accuracy. From this flood of information, the emergence of an interstellar visitor is inferred from the detection of a single, anomalous point of light, an object moving at a speed and in a direction inconsistent with objects bound by the sun's gravity. Atlas is just one voice among many in a planetary-wide network of automated sky surveys. The Catalina Sky Survey in Arizona, the Lincoln Near-Earth Object linear program in New Mexico, and the NEOWISE mission orbiting high above Earth's atmosphere all contribute to a relentless, never-sleeping watch. Together, these systems form an interconnected web of sensors that continually scan the heavens, ensuring that no transient object or unexpected movement escapes notice. Their collective efforts have transformed the way we discover and track objects from beyond our solar system, turning the once rare discovery of interstellar visitors into a more routine, if still extraordinary, pursuit. In the case of Swan R2, the detection was initially made not by professional astronomers but by Vladimir Bezugly, an amateur astronomer whose dedication and keen eye led him to notice an unusual brightening in imagery from the Solar and Heliospheric Observatory, SOHO. This early warning illustrates a fundamental aspect of modern astronomy, the synergy between human intuition and machine precision. While automated surveys cast their wide nets across the sky, it is often the observant eye of an amateur or a dedicated researcher that catches the first hint of something extraordinary, an anomaly that, once confirmed, can become a subject of intense scientific scrutiny. From the faintest points of light to detailed spectroscopic signatures, the process of discovery involves a complex interplay of technology, and when the Solar and Heliospheric Observatory's SWAN instrument first captured data indicating the presence of a new object, it was not NASA's professional astronomers who initially recognized its significance. Instead, it was Vladimir Bezugly, an amateur astronomer diligently examining SWAN imagery for his own research, who spotted an unusual brightening, a subtle anomaly that would soon become known as one of the most spectacular comets of the year 2025. This moment exemplifies the way modern astronomy functions in the 21st century. It is a collaborative effort where professional and amateur observers, Advanced silicon sensors and human intuition work side by side to identify fleeting phenomena slipping into our cosmic neighborhood. The instruments themselves whisper their secrets through the language of photon counts and pixel intensities, silent messengers encoding the presence of something new. Yet it is human insight that recognizes when these whispers signal something truly extraordinary, prompting further investigation. Different types of astronomical instruments unlock different truths about these celestial visitors. Visible light cameras, for example, provide a broad picture. They reveal the overall structure of the object, including the brightening nucleus, the expanding cloud of gas, known as the coma, and the sweeping tail that extends away from the sun, behaving like a cosmic weather vane pushed by solar winds. These images tell us about the physical appearance and immediate activity of the comet, but to truly understand what these objects are and what they might contain, we need to delve deeper into their light, breaking it apart into its constituent colors through the science of spectroscopy. Spectroscopy transforms the raw light captured by telescopes into detailed information about the comet's composition. When molecules in the coma, the gaseous envelope surrounding the nucleus, absorb solar radiation and then re-emit it, they produce distinctive spectral fingerprints. These emission lines serve as chemical signatures, allowing scientists to identify the specific molecules present. When the Very Large Telescopes directed their powerful instruments at 3I Atlas, they uncovered unexpected details that challenged existing assumptions. For instance, they detected strong emission lines from cyanogen, a molecule known to fluoresce in the presence of sunlight, and more surprisingly, from nickel atoms glowing in the vacuum of space. While the presence of nickel in comets has been noted before, it is not common enough to ignore, and its detection in this context raised eyebrows among researchers. What makes these observations even more intriguing is what was not detected. The spectrographs showed no sign of iron emission lines, which typically accompany nickel signatures in natural samples. The absence of iron, coupled with the prominent nickel signals, created a peculiar chemical fingerprint that did not align with our standard models of how comets form and evolve. Such anomalies prompted scientists to reconsider their assumptions about the composition and history of this interstellar visitor. Meanwhile, in August of 2025, the James Webb Space Telescope turned its infrared eyes toward 3I Atlas. Its observations revealed a composition dominated by carbon dioxide, with relatively little water vapor at the large distances from the sun at which these measurements were taken. This profile is consistent with a comet whose outer layers are rich in volatile ices that sublimate, that is, transition directly from solid to gas at lower temperatures. Such ices can produce activity far from the sun, well before water ice begins to sublimate and contribute significantly to the coma. Adding yet another perspective, the Swan imagery from the Solar and Heliospheric Observatory offers insights into the distribution of water vapor around the comet. The instrument maps hydrogen atoms, which are produced when water molecules are broken apart by solar ultraviolet radiation. This three-dimensional view reveals how water vapor spreads through the space surrounding an active comet, details that are invisible to conventional telescopes. Such mappings provide crucial information about the behavior of water in the comet's environment, helping scientists understand the sublimation processes and the composition of its outer layers. High-resolution imagery from the Hubble Space Telescope further constrains the size of 3I Atlas's nucleus, suggesting it measures only a few kilometers across. This size is substantial enough to generate the observed activity, but small enough to have eluded detection until the comet was already well within our solar system. The data collectively paint a picture of a tiny but dynamically active object, its small nucleus capable of producing the expansive coma and tail observed from Earth. Together, these diverse observations, from visible imaging and infrared spectroscopy to ultraviolet mapping, compose a complex and intriguing portrait of this interstellar visitor, challenging existing models and expanding our understanding of such objects originating beyond our solar system. Every new observation adds an essential fragment to a puzzle that increasingly grows in intricacy with each collected data set. Yet it's crucial to recognize that instruments, powerful as they are, can sometimes deceive just as easily as they can reveal. The automated processing systems tasked with analyzing telescopic imagery are meticulously crafted to detect familiar patterns, the predictable behaviors of celestial objects moving along Keplerian orbits around the Sun. These systems excel at recognizing what should be there, at filtering out the ordinary, and at flagging deviations that might hint at something extraordinary. However, when an object behaves differently, even in subtle ways, those very algorithms designed to bring clarity can inadvertently mask the true nature of the anomaly. Take, for instance, the challenge of measuring how an object's brightness changes over time. Comets, for example, do not simply grow brighter at a steady, uniform rate as they near the Sun. Instead, their luminosity often fluctuates through complex variations driven by multiple factors. These include the sublimation of different ices at varying distances from the Sun, the rotation of nuclei with often irregular shapes, and the episodic release of dust and gas from active regions on their surfaces. Such natural variability can resemble signs of something unusual, making it a daunting task for scientists to distinguish between the normal and the genuinely anomalous. This complexity becomes even more evident when considering the observed green coloration in the comet designated as 3I Atlas. The vibrant hue showcases the subtleties involved in interpreting spectroscopic data. Several molecules have the capacity to produce green emission under the specific conditions present in cometary comas. The most common culprit is diatomic carbon, which fluoresces a vivid green when excited by solar radiation. Cyanogen, a molecule composed of carbon and nitrogen, can also contribute to the green glow. Without high-resolution spectroscopy, an advanced technique capable of definitively identifying the precise molecules responsible, the green tint remains a suggestive clue rather than a diagnostic signature. It hints at the chemical processes at play but does not conclusively reveal the comet's composition. Media coverage of such unusual astronomical discoveries often amplifies uncertainty into sensational headlines. When initial reports highlight unexpected chemical signatures or peculiar orbital characteristics, these details can be prematurely interpreted as evidence of extraordinary phenomena, whether artificial or otherwise, long before the peer review process has validated or challenged these findings. This rush to judgment can distort the scientific narrative, turning preliminary data into compelling but unverified proof of something extraordinary. It's important to understand that the scientific method is inherently self-correcting, designed to refine and clarify our understanding over time. However, this correction process often unfolds at a pace that can seem painfully slow compared to the rapid appetite for answers generated by public interest and media speculation. During this interval, instruments serve a critical role not merely as detectors of cosmic phenomena, but as steadfast anchors to reality amidst an ocean of conjecture. Telescopes, after all, do not possess desires or biases. They simply record photons and measure positions, gradually building a comprehensive database of observations. Over time, this data will allow scientists to piece together a clearer, more accurate picture of the visitors from space. Safety considerations also shape and constrain our observational efforts. Both 3I Atlas and Swan R2 follow trajectories that maintain safe distances from Earth, ensuring that these objects pose no threat to our planet. For instance, 3I Atlas is projected to approach no closer than about 1.8 astronomical units, roughly 270 million kilometers, while Swan R2's closest approach will still be more than 40 million kilometers away. at approximately 0.27 astronomical units. These distances are vast, ensuring that we are not in danger, but they also provide invaluable opportunities to study objects that originated under conditions vastly different from those of our solar system. The primary challenge now lies in timing. As October of 2025 unfolds, both visitors will sink deeper into the solar glare as seen from Earth. This celestial cloak gradually obscures their visibility, complicating efforts to observe and understand them during their most critical close approach phases. Despite the challenges posed by the tight schedules, the distances involved, and the limitations of our instruments, each observation, even the faintest, serves as a vital piece of the broader scientific puzzle. As ground-based telescopes gradually lose sight of their targets during the most critical moments of the object's approach to the Sun, their space-based counterparts, though better equipped, must contend with finite observation windows and competing scientific priorities. What unfolds from this ensemble of instruments is a detailed mosaic composed of myriad data points, spectral lines, orbital parameters, and brightness variations. A complex tableau that invites many interpretations. Yet amid this intricate tapestry, a pressing question persists. What if the initial deception lay not with the celestial objects themselves, but with the very tools we rely upon or the expectations shaping our readings? Throughout this celestial vigil, telescopes will persist in their relentless accumulation of photons, measuring positions and spectral signatures with mechanical precision honed over decades. But as these visitors gradually descend behind the sun's blinding glare, their whispers, encoded in faint electromagnetic signals, will grow increasingly hushed, leaving us to ponder the secrets concealed within the growing silence. This silence marks the transition into what we might call the language of metals, a dialect spoken in the vocabulary of atoms and molecules, yet one that can carry messages written in unexpected ways. When the most powerful spectrographs of the Very Large Telescope turned their gaze toward this interstellar visitor, they uncovered findings that compelled a profound recalibration of our expectations. In particular, astronomers observed the presence of nickel vapor shimmering in the near-vacuum environment surrounding the comet's nucleus, a glow that appeared unaccompanied by the ion emissions that standard models predicted should be present. In the realm of spectroscopy, every element leaves behind a unique spectral fingerprint, a set of specific wavelengths emitted when atoms are excited by solar radiation or collision processes. These fingerprints serve as elemental signatures, as distinct and recognizable as the genetic code in biological DNA. Nickel atoms, when excited, produce emission lines predominantly in the green portion of the spectrum, contributing to the ethereal hue that has made 3I Atlas a favorite among astrophotographers and skywatchers. However, in the broader cosmic context, nickel rarely appears alone, especially in the environments of meteorites, asteroids, and the handful of comets where it has been previously detected. Typically, nickel coexists with ionized elements, most notably iron, in ratios that reflect the nuclear processes that forged these elements in the stellar cores billions of years ago. These abundance patterns, etched into the very fabric of the periodic table, suggest a cosmic consistency. Where nickel is found, iron should follow in predictable proportions, a signature of natural stellar nucleosynthesis. Yet 3I Atlas seems to have sidestepped that fundamental lesson. As the comet neared its brightness peak in August 2025, the Very Large Telescope's observations revealed strikingly strong nickel emission lines that stood out clearly against the spectral background. Intriguingly, the same observations aimed at detecting ionized species found essentially nothing. The upper limits placed on ion presence were so low that, if ion were present at the expected cosmic abundance ratios, it should have been easily detectable. This stark discrepancy has ignited a host of theoretical explanations, each striving to reconcile the observations with known physical laws. One possibility proposes that organic compounds bearing nickel, stable in the frigid environment of interstellar space, may undergo breakdown under the intense heating of solar proximity, releasing nickel atoms preferentially. Alternatively, it is suggested that long-term space weathering processes, operating over millions of years, could have altered the comet's surface chemistry in ways we do not yet fully comprehend, selectively enriching nickel in the outer layers or modifying its expected relationships with other elements. In essence, the chemical signature of 3I Atlas challenges our understanding of cosmic chemistry, hinting at processes or histories that diverge from the typical stellar and planetary formation narratives. Such anomalies invite us to reconsider the assumptions underpinning our models, whether they pertain to the composition of interstellar objects or to the very pathways through which matter evolves in the cold depths of space. The universe is not bound by our expectations or assumptions about how elements should behave or interact. When it comes to the chemical compositions of interstellar objects, nature often writes its own rules, rules that can surprise even the most advanced telescopic observations. Take, for example, the previous interstellar visitor, comet 2I Borisov. Analyzing this celestial wanderer with the world's most powerful telescopes revealed intriguing chemical oddities. Its ratio of carbon monoxide to water diverged markedly from what we observe in comets originating within our own solar system. Such a discrepancy strongly suggested that Borisov had formed in a much colder environment, perhaps in a region around its parent star that was rich in carbon monoxide and significantly colder than the regions where most solar system comets are thought to originate. But Comet 3I Atlas pushes these chemical mysteries into even more fascinating territory. When the James Webb Space Telescope turned its infrared sensors toward this interstellar visitor, it revealed a composition dominated primarily by carbon dioxide. Surprisingly, water vapor, a molecule usually abundant in comets, was playing a relatively minor role at the large distances from the Sun where these measurements were made. This pattern indicates that carbon dioxide is leading the parade of volatiles sublimating from the comet's surface, with water only beginning to become prominent as the comet draws closer to the Sun. Such a sequence hints at a layered, onion-like internal structure, where the most volatile ices are layered on the outside, ready to sublimate at lower temperatures while less volatile compounds are tucked deeper within. Adding another layer to this chemical portrait is cyanogen, a molecule likely responsible for much of the comet's vivid green hue that has captivated public fascination. Spectroscopic observations show prominent emission lines of cyanogen in the spectrum. These lines are consistent with organic compounds being broken apart by the intense ultraviolet radiation from the Sun, a process known as photodissociation. However, the relative strengths of these emission features do not quite match what we see in typical solar system comets, implying subtle but meaningful differences in composition or structural makeup. The green coloration, which has drawn so much attention, carries its own set of mysteries. While diatomic carbon is frequently cited as the primary cause of green emission in comets, the specific molecules or excited states responsible for the verdant glow of 3I Atlas remain uncertain. Cyanogen can contribute to green emission, but so can certain excited states of carbon molecules, making the true source ambiguous without ultra-high-resolution spectroscopy. These chemical signatures do more than merely describe the comet. They challenge our ability to classify and understand such objects in simple terms. If atoms are like letters and molecules like words, then 3I Atlas writes in a dialect heavily flavored with carbon dioxide and subtly accented with metallic elements. An unconventional language that doesn't quite follow terrestrial grammatical rules. This unusual composition makes perfect sense in the context of star system formation around other stars. yet it is distinctive enough to draw significant scientific interest. The production rates of various gases as the comet approaches the Sun offer another vital clue. Observations show that, predictably, as 3I Atlas moves closer, the rate at which it releases different molecules increases. This trend aligns with the well-understood physics of sublimation. The closer a comet gets to the Sun, the more rapidly its frozen ices transition directly from solid to gas. The mathematical models describing this process are reliable and well-tested, enabling astronomers to forecast future activity levels based on current data. Still, within this predictable framework, subtle anomalies persist. The ratios of different molecular species in the comet's outgassing do not perfectly match the models based on familiar solar system comets. These minor discrepancies suggest that 3I Atlas may have a unique internal composition or structural makeup, perhaps reflecting formation conditions in a star system vastly different from our own. Such anomalies, while seemingly small, open new avenues of inquiry into the diversity of planetary building blocks and the chemical pathways that operate in distant stellar nurseries. The variations observed in the brightness curve of this celestial visitor suggest a complex and intriguing story hidden within its surface composition. These fluctuations could indicate that the nucleus itself possesses regions of differing material makeup, what scientists call compositional heterogeneities, implying that not all parts of the nucleus are uniform. Alternatively, these irregularities might result from sudden bursts of outgassing, streams of gas and dust, discharged in discrete events possibly triggered by subsurface processes that remain largely speculative at this stage. Such processes could involve internal heating, structural fractures, or other mechanisms beneath the surface, yet our understanding of these triggers remains limited. The amateur astronomy community has played an unexpectedly vital role in unraveling these chemical enigmas. Across the globe, dedicated backyard observers equipped with modest telescopes and imaging tools have captured high-quality photographs that track the evolving structure of the coma, the cloud of gas and dust surrounding the nucleus, and the morphology of the tail. These observations, often conducted during moments when professional telescopes are constrained by busy schedules and competing research priorities, provide invaluable temporal coverage. They allow scientists to monitor changes continuously over days and weeks, filling in gaps that would otherwise be missed. In the age of social media, these early and often preliminary scientific findings have become amplified, sometimes transforming cautious interpretations into sensational headlines. For example, the peculiar observations of nickel emissions lacking the expected associated ion signatures have been sensationalized by some as evidence of artificial construction, metallic components deliberately engineered rather than naturally formed. This leap into the realm of speculation, however, extends far beyond what the spectroscopic data can reliably support. The spectroscopic signatures, while unusual, do not conclusively point to artificial origins. Rather, they could be explained by natural processes, especially considering the diverse conditions under which objects from other star systems might form. Official positions from space agencies remain conservative and grounded in scientific consensus. NASA, for instance, maintains that current data are consistent with a naturally occurring comet, albeit one exhibiting some unusual yet not unprecedented chemical features. Their scientists emphasize that objects formed around different stars are expected to display a variety of chemical compositions, shaped by varying temperatures, pressures, and elemental abundances during their formation. Such differences can produce signatures unlike those typical within our own solar system, which does not necessarily imply artificiality. The European Space Agency shares a similar perspective. Through its extensive array of missions and ground-based observing campaigns, ESA scientists acknowledge the spectrum's peculiarities but assert that the fundamental physics underpinning cometary activity such as sublimation of ices, release of gas and dust, offers a coherent and natural explanation for what we observe. These processes are well understood within the framework of comet physics, and no need arises to invoke exotic or artificial scenarios. Nonetheless, scientific progress depends on scrutinizing anomalies carefully. The chemical curiosities displayed by this visitor, from nickel emissions to the dominance of carbon dioxide and the signatures of cyanogen, provide a rich puzzle that will keep researchers engaged for years. Each new piece adds nuance, perhaps revealing insights into the formation of stellar systems elsewhere in the galaxy, or teaching us more about the diversity of objects that traverse interstellar space. As October of 2025 advances and the comet approaches what is known as solar conjunction, when it sinks behind the Sun from Earth's perspective, the window for detailed spectroscopic analysis narrows. The increasing distance and the decreasing solar elongation, the angle between the Sun and the object as viewed from Earth, will eventually render ground-based telescopes incapable of capturing further data until the comet re-emerges months later, if it indeed makes another appearance. In essence, we are deciphering a language spoken in a dialect of ice and metal, a dialect that might speak of conditions in the stellar nurseries where this object formed, perhaps hundreds of light-years away. Whether this chemical language adheres strictly to the known grammar of physics and chemistry as understood on Earth, or hints at something more deliberately engineered, an artificial construct, remains the central mystery of our October sky. These chemical signatures are like pages from a cosmic manuscript, offering clues but also raising profound questions about the origins of such objects and the processes that shape them. As our observational capabilities diminish, the true story of this visitor remains tantalizingly out of reach, yet it continues to inspire curiosity about the fundamental nature of our universe. Atoms in their silent honesty reveal truths about the universe, yet they often leave us yearning for deeper understanding, insights that extend beyond their immediate signatures. In the realm of cosmic exploration, the story becomes even more intricate. Imagine then the grand design of our solar system as an elaborate celestial clockwork, an intricate mechanism where each planet moves along its predictable elliptical orbit around our central star, obeying the precise laws of gravity. Meanwhile, the countless smaller bodies, asteroids, comets, and occasionally interstellar visitors, trace trajectories that twist and diverge, intersecting and diverging in a cosmic dance dictated by the complex mathematics of gravitational mechanics. Now, picture two such cosmic voyagers arriving from entirely different corners of space, each following distinct and independent paths. One might be a hyperbolic interloper, rushing in from the depths of interstellar space, while the other is a long-period comet, originating from the distant and frigid Oort cloud, only now being nudged inward by gravitational tugs. What is astonishing and almost unfathomable is that both these visitors, so fundamentally different in their origins and journeys, are scheduled to make their closest approach to our Sun within mere weeks of each other. The odds of such a coincidence based purely on random chance should be vanishingly small, an event so rare that it strains the boundaries of probability itself. Yet here we stand, in the crisp clarity of October in the year 2025, witnessing this remarkable spectacle unfold directly above us. It was in early July that our observations first identified 3I Atlas, an interstellar object emerging from the direction of the constellation Serpent's Corner. Its discovery marked a pivotal moment, signaling that this visitor had become luminous enough for our automated sky surveys to detect its faint glow amidst the vast darkness. The orbit it traced was hyperbolic, an unmistakable signature that this object was not gravitationally bound to our Sun, merely passing through our solar neighborhood on a fleeting journey. The orbit carried a steep inclination of roughly 175 degrees, meaning it was traveling retrograde relative to the planet's motions. Approaching from beneath the ecliptic plane, like a cosmic salmon swimming upstream against the prevailing currents of planetary motion, it seemed almost to defy the familiar paths we associate with native solar system bodies. In stark contrast, Swan R2 told a different story altogether. This object belonged to the class of long-period comets, typical visitors from the distant Oort cloud, spending most of their existence in the outer reaches of the solar system's icy frontier. These comets are nudged inward over time, their journeys governed by the slow, relentless pull of gravity, only to be awakened from their frozen slumber when solar heating begins to vaporize their icy nuclei, igniting their spectacular tails. Swan R2 was discovered near the constellation Virgo, emerging from the solar glare that had once concealed it during its approach. Its geometrical discovery provided crucial clues about its nature, highlighting the challenge of observing such objects, which often spend months or even years in regions of the sky too close to the sun for effective detection. By the time Atlas had identified its interstellar visitor, this cosmic wanderer had already passed beyond the orbit of Jupiter, showing preliminary signs of cometary activity, an indication that it was responding to the sun's warmth. The difference in their discovery timelines is rooted in observational biases, particularly the so-called Hallech effect. Long-period comets tend to brighten dramatically as they near the sun, yet this increase in brightness often occurs when they are still at small angular distances from the star as seen from Earth. Their proximity to the sun renders them invisible in the glare, remaining hidden until their orbits carry them far enough away from the Sun-Earth line to be visible in twilight skies. That was precisely the case with Swan R2 in September of 2025. Its perihelion, the closest point to the Sun, occurred on the 12th of September, during which it plunged within half an astronomical unit, or roughly 46 million kilometers, of our star. This timing set the stage for a remarkable celestial convergence, a cosmic schedule that, to the untrained eye, seemed almost as if someone had meticulously planned this rendezvous. Meanwhile, the interstellar visitor Atlas was already on its inward trajectory, approaching perihelion around late October, with its closest approach to the Sun anticipated within a few days, on roughly the 29th or 30th of October. The synchronized timing of these two objects, one a fleeting interloper from beyond our solar system, the other a native comet awakened from the distant icy depths, raises profound questions. Are these mere coincidences, or do they hint at some underlying cosmic choreography? The universe, in its vastness, often appears to follow no pattern, yet occasionally it presents us with moments that challenge our understanding. Moments that seem to align with purpose rather than randomness. Thus, as we observe these cosmic visitors, each with its own origin story and on the horizon of October, two remarkable cosmic visitors are set to reach their closest points to key celestial bodies within our solar system, in a sequence that defies mere coincidence. First, the interstellar object known as 3 Atlas is scheduled to make its nearest approach to Mars on the 3rd day of October. During this close flyby, it will pass within approximately 30 million kilometers of the red planet, offering a rare opportunity for detailed observation by our robotic explorers orbiting Mars. Meanwhile, around the 21st of October, Swan R2 will reach its own perihelion, coming within roughly a quarter of an astronomical unit, about 40 million kilometers, of our star, the Sun, an approach that places it just inside the orbit of Mars. Adding to this intriguing alignment, 3 Atlas will itself arrive at its perihelion, a point of closest approach to the Sun, around the 30th of October, coming within approximately 1.35 astronomical units. This means it will be approaching the Sun from a distance just inside the orbit of Mars, igniting a flurry of scientific curiosity about its composition and activity. What makes these events even more compelling is the tight clustering of all these significant orbital milestones within a span of just 6 weeks. Such a concentrated sequence of close encounters would, under the assumption of randomness and uniform distribution over cosmic timescales, be exceedingly improbable. The odds of 3 separate objects from different origins reaching such proximity to key bodies in our solar system within such a narrow window stretch the limits of what we might expect from sheer chance alone. Yet, as the principles of statistical mechanics tell us, events that seem astronomically unlikely can, given enough opportunities and sufficient time, become almost inevitable. In a universe teeming with billions of comets, asteroids, and the occasional interstellar visitor, we might simply be witnessing one of those rare moments, a cosmic roll of the dice, where the outcome aligns in an unexpectedly ordered pattern. The contrast between these two visitors extends far beyond their origins and their orbital paths. 3 Atlas appears as a slender, needle-like point of light, its activity confined to a relatively small region surrounding its nucleus. Current estimates suggest that its core, its nucleus, is perhaps only a few kilometers in diameter. While modest compared to the giants of our own solar system's cometary population, this size suffices to produce the observable coma, a diffuse cloud of gas and dust, and a tail that streams behind it as it approaches the sun. In stark contrast, Swan R2 is a cosmic spectacle of enormous proportions. Its coma spans several degrees of the sky when viewed through binoculars, and experienced observers have reported its tail extending up to 2 degrees in length, an impressive vista measuring millions of kilometers across. This gossamer structure is so tenuous that its density is comparable to the vacuum of a laboratory, yet it remains visible across interplanetary distances because of its vast volume. Its delicate, almost poetic form dances against the changing backdrop of Earth's seasons. As autumn advances in the northern hemisphere, both objects gradually sink lower toward the western horizon after sunset. Swan R2 dominates this celestial tableau, easily observable with a decent pair of binoculars and a clear view toward the constellation Virgo. Meanwhile, observing 3 Atlas requires more sophisticated equipment, but its distinctive greenish hue makes it unmistakable once located in the sky. October, however, presents a mix of challenges and opportunities for astronomers. The same geometrical arrangements that bring these objects into such close proximity to the Sun also complicate their observation from Earth. As both objects approach their perihelion points, the closest positions to the Sun, they sink deeper into the Sun's bright glare, making detailed observation increasingly difficult. This growing solar glare will, in time, cause ground-based telescopes to lose sight of the objects altogether during their most scientifically critical phases, moments when they are closest to the Sun and most active. This phenomenon results in what is known as an observational blackout, creating a crucial gap in our knowledge. This missing window may hold the key to understanding what these visitors are truly made of, whether they are natural bodies or something more exotic. The inability to track these objects during their perihelion passages poses a significant challenge, as it deprives us of vital data needed to unravel the mysteries they carry. Mysteries that could redefine our understanding of the dynamic processes shaping our cosmic neighborhood. During the upcoming weeks, when Earth's telescopic eyes will be unable to monitor them due to the intense glare of the Sun, both celestial objects will be subjected to their maximum thermal influence from solar radiation. If any extraordinary phenomena are destined to unfold, or if some concealed features are to surface, these silent weeks are the most likely window for such events to occur. The challenge lies in the fact that their most critical encounters with the Sun, and any potential surprises, will happen behind the Sun's luminous veil, rendering direct observation impossible at the very moment when the most revealing processes might take place. Adding to the complexity of their trajectories is the peculiar retrograde motion exhibited by 3I Atlas. Unlike objects orbiting in the same direction as the planets, this object moves in a reverse path relative to the general orbital motion of our solar system's planets. This retrograde behavior introduces an additional layer of intricacy into its orbital mechanics. Bodies traveling in retrograde trajectories experience different gravitational influences and perturbations compared to their prograde counterparts. These subtle gravitational nudges can influence their long-term paths in ways that are often barely perceptible but nonetheless measurable with precise tracking. By carefully monitoring these minute deviations before and after the Sun's close encounter, scientists can derive valuable insights into the mass and internal composition of the visitor. If they can achieve sufficiently accurate positional data, during this pivotal period, Mars will act as an advanced observational platform, a forward-looking sentinel in our pursuit to understand 3I Atlas. As the object approaches its nearest point to the Sun on October 3rd, Mars's orbiting spacecraft, missions primarily tasked with studying Martian weather patterns and geological features, will pivot their instruments toward this passing visitor. Though these observations are not part of a dedicated campaign but rather opportunistic in nature, they might become our only unclouded glimpse during the critical solar approach phase. The suite of instruments aboard these Martian spacecraft, spectrometers, high-resolution imagers, and other sensing tools, could potentially resolve details that are simply beyond the reach of terrestrial telescopes, uncovering the structure of the comet's coma and the development of its tail from perspectives unobstructed by Earth's atmospheric distortion. Furthermore, the European Space Agency has announced coordinated plans to utilize Mars-based assets, including the ExoMars Trace Gas Orbiter and other orbiters around the Red Planet. Equipped with advanced spectroscopic and imaging systems, these spacecraft are capable of detecting and resolving fine details of the comet's activity that terrestrial instruments might miss. During the flyby, the viewing geometry from Mars will be especially favorable, offering unique angles on the structure of the coma and the tail's formation, complementing and enriching the data gathered from Earth. Such multi-vantage point observations could help piece together a more comprehensive picture of the object's physical state and activity. Yet despite these multiple viewpoints and the sophistication of our observational tools, some fundamental questions continue to linger unresolved. The precise timing of these encounters and the peculiarities in their trajectories persist as enigmas for researchers, especially those who have dedicated their careers to understanding the statistical mechanics governing our solar system's dynamics. In a universe where chance encounters can span millions of years, it remains perplexing that we are witnessing two such markedly different visitors arriving within a matter of weeks. This coincidence prompts a profound question. If these paths are not purely random, are they the result of some hidden plan or design? Is their arrival a poetic coincidence, or could it be an orchestrated event, a sign of a larger cosmic choreography that we are only beginning to comprehend? This pondering leads us into the realm of speculative theories, crafted like constellations in the night sky, where human minds, naturally inclined to seek patterns, attempt to impose meaning upon apparent chaos. When confronted with two enigmatic visitors arriving so closely in time, both exhibiting unusual features and seemingly following a synchronized schedule, our instinct is to weave narratives that extend well beyond the raw data. These stories span a spectrum from the merely exotic, suggesting natural, albeit rare, cosmic phenomena, to the profoundly extraordinary, hinting at deliberate technological intervention. One prominent hypothesis proposes that 3I Atlas is not a mere natural object, but an advanced reconnaissance probe, an intelligent, swift, and maneuverable craft sent to survey our solar system's resources and defenses. In this scenario, Swan R2 functions as a primary installation, an adaptable mobile base or relay station, supporting extended operations within the inner solar system. It could serve as a communications hub, a resource depot, or a command center, capable of facilitating long-term surveillance, data collection, and perhaps even interaction with the environment or other objects. This fortress-like role positions Swan R2 as a strategic asset designed to support or oversee a broader mission, potentially orchestrated by an intelligent civilization with the technological prowess to deploy and operate such complex systems across interstellar distances. The synchronized timing of their arrivals is no mere coincidence. Rather, it appears to be a deliberate coordination, signaling the presence of a broader, long-term mission that likely originated many years, perhaps even decades prior. This mission seems to have been launched from the remote, cold depths of space, the vast, silent regions that lie between the stars, where ancient, automated systems might still be quietly operating. One compelling interpretation suggests that both objects are remnants of an elaborate infrastructure, a vast and enduring network of machinery designed to maintain, service, or update critical systems scattered across our galactic neighborhood. These are not random wanderers, but parts of a long-standing methodical routine following predictable cycles to carry out their duties. In this scenario 3, the interstellar object designated Atlas could be a vessel carrying software updates, firmware patches, or vital replacement components, akin to a cosmic courier delivering essential technological refreshes. Meanwhile, Swan R2 might function as a manufacturing hub or power source, equipped to carry out significant overhauls, repairs, or upgrades on a grand scale. In this light, our solar system is merely one stop along their extensive service route, a routine waypoint in a journey spanning millions of years. This concept aligns with the idea of an ancient patrol, a vigilant monitoring network established long ago by a civilization concerned with overseeing the development of potentially dangerous or advanced intelligences. Such a civilization, having observed the emergence of complex life and technological prowess in various star systems, might have set in motion a silent, enduring watch, dispatching these automated agents to assess, gather intelligence, or even intervene if necessary. As humanity's radio, television, radar, and satellite emissions have increasingly leaked into space over the past century, these dormant systems, perhaps long dormant, could have been reactivated by the signals we emitted. Acting as triggers, they might have dispatched reconnaissance elements along with more substantial platforms to evaluate whether our burgeoning technological civilization posed a threat or an opportunity. Some theorists go even further, proposing that these objects are a calculated response, an answer to a message we inadvertently sent into the cosmos. Our expanding electromagnetic bubble, created by decades of broadcasts, radar pulses, and satellite communications, extends outward at the speed of light, creating a shimmering envelope of signals around Earth. If an intelligent distant observer has been listening, if they've been tuning in, then the arrival of 3 Atlas and Swan R2 might be their way of replying, not randomly, but as part of a deliberate, informed response to our recent technological awakening. This leads us to what is called the relic technology hypothesis, the idea that these objects are artifacts of human creation, launched during a future era when our descendants had achieved true interstellar capability. Perhaps, in a distant future, humanity sent these artifacts back in time, using trajectories designed to arrive precisely at moments when they could influence or observe their origins. The unusual chemistry and orbital traits of the objects could reflect manufacturing techniques or advanced material sciences that go beyond our current understanding, yet still bear unmistakable signatures of human origin. Throughout history, cultures across the Earth have woven stories of celestial harbingers, comets, and strange astronomical phenomena that presaged upheavals, the rise or fall of kingdoms, or the coming of prophets. These lights in the sky have long served as symbolic markers of transition and transformation. It's possible, then, that 3 Atlas and Swan R2 are modern embodiments of these archetypal symbols, cosmic punctuation marks signaling a new epoch in human development, or perhaps a pivotal moment of change in our collective journey. On a darker note, some interpret these objects through a more ominous lens, seeing in them a predator and guardian dynamic. If 3 Atlas represents a threat, a weapon system, invasion probe, or reconnaissance device designed for hostile purposes, then Swan R2 could be a protective response. It might be deployed by the same civilization that sent Atlas, acting as a safeguard, a defensive measure to neutralize or contain the potential danger before it can reach Earth. Alternatively, Swan R2 could belong to a different intelligence altogether, dispatched with the intent to intercept or counteract the threat posed by Atlas, effectively serving as a cosmic security measure. In this view, the entire scenario resembles a silent, extended confrontation, an interstellar game of chess played out across eons, where each object's purpose is woven into a grand, unseen strategy. Whether as part of a long-term monitoring effort, a defensive posture, or a response to humanity's own signals, these objects embody a complex narrative of cosmic vigilance and perhaps cosmic conflict. The convergence of celestial objects in October of 2025 transforms the night sky into a kind of cosmic battleground, with Earth unknowingly positioned as the potential prize. This rare alignment has fueled a range of speculative theories, partly because they address a fundamental limitation inherent in traditional astronomy: the assumption that any unusual phenomena must be explained through natural physical processes. While this cautious stance has historically propelled scientific progress, leading to groundbreaking discoveries about stellar evolution, black holes, and the nature of our universe, it also introduces certain blind spots. These are spaces where extraordinary possibilities, those that challenge conventional understanding, are often dismissed not because evidence contradicts them, but because they fall outside the boundaries of accepted theoretical frameworks. One prominent advocate for considering these unconventional ideas is Avi Loeb, a Harvard astrophysicist whose bold hypotheses have garnered international attention. Loeb, notable for suggesting that the interstellar object known as Oumuamua could be an artificial construct, has extended similar reasoning to the case of the interstellar visitor designated as 3I Atlas. He highlights several anomalies: the unusual chemical signatures detected in its coma, the precise timing of its approach relative to the Sun, and what appears to be a coordinated movement pattern with Swan R2. These features, he argues, could be indicative of technological origins rather than natural formation, prompting a re-evaluation of what constitutes normalcy in interstellar object behavior. Loeb emphasizes that extraordinary claims demand extraordinary evidence, a principle that underpins scientific rigor. Yet he also contends that when such compelling evidence does emerge, it warrants serious and open-minded consideration, opening the door to possibilities that might otherwise be overlooked. Meanwhile, official space agencies such as NASA and the European Space Agency tend to adopt a more conservative stance. They maintain that current observations, despite their intriguing characteristics, are consistent with known natural phenomena. These agencies emphasize that our catalog of confirmed interstellar visitors remains very limited, only 3 objects over the past 6 years, making it difficult to establish a baseline for what is typical or anomalous within this population. This scarcity of data complicates efforts to differentiate between natural outliers and potential signs of alien technology. This ongoing debate reflects deeper questions about the scientific method itself and the very nature of evidence. How anomalous must an observation be before it challenges our core assumptions about the universe? When should scientists entertain hypotheses that seem to defy established physics? And how do we balance the need for skepticism with the possibility of revolutionary discoveries? The media, eager to capture public interest, often amplifies certain aspects of these debates, highlighting sensational details like the nickel without iron signature in the spectroscopic data, while downplaying or oversimplifying more nuanced scientific puzzles. For example, the so-called nickel without iron anomaly has received widespread attention on social media platforms, fueling speculation about industrial processes, artificial manufacturing signatures, or even extraterrestrial engineering. Claims that extend well beyond what the spectroscopic evidence actually supports. In contrast, the more scientifically grounded observations, the unusual volatile composition of 3I Atlas, its precise orbital timing, and the apparent coordination with Swan R2, tend to receive less media coverage despite being supported by robust data. These puzzles challenge our understanding of cometary chemistry and celestial mechanics, yet they are often overshadowed by sensationalized narratives. Adding to the complexity is the role of human psychology, particularly our innate tendency toward conspiracy thinking. Humans are naturally predisposed to perceive agency and intention in events that occur randomly or are merely coincidental, especially when those events bear implications for our future or sense of control. The idea that cosmic visitors might be deliberately sent rather than accidental passers-by satisfies a deep-seated psychological need for meaning and mastery over chaos. This desire to find purpose in the seemingly random universe fuels the spread of theories suggesting that these objects are not just natural phenomena, but signals or probes from an intelligent civilization, an idea that resonates with our collective need for understanding and connection in an otherwise incomprehensible cosmos. Historical examples serve as both cautionary tales and sources of inspiration when it comes to interpreting extraordinary phenomena in astronomy. Throughout history, many groundbreaking discoveries, such as the shift from geocentric to heliocentric models, the recognition of black holes, or the identification of exoplanets, initially met with skepticism by the scientific establishment. These moments of doubt were often rooted in the prevailing paradigms, which required substantial evidence before accepting revolutionary ideas. Yet, over time, persistent investigation and accumulating data have transformed these once controversial concepts into foundational knowledge, fundamentally reshaping our understanding of the universe. Nevertheless, the history of science also offers a sober reminder. Extraordinary claims, no matter how compelling, must be supported by equally extraordinary evidence. Without such rigorous backing, novel hypotheses tend to fade into obscurity, their initial intrigue waning as critical scrutiny prevails. These cautionary tales underscore the dangers of premature speculation, which can divert scientific progress or foster misconceptions if not tempered by disciplined inquiry. The convergence of the celestial objects designated as 3I Atlas and Swan R2 in October of 2025 presents a unique opportunity to put these lessons into practice. Scientists are poised to test competing hypotheses against real, tangible data. If both are merely natural comets obeying the well-understood laws of physics, their behavior during perihelion, the point in their orbits closest to the Sun, should align closely with established models of ice sublimation and dust emission. Such models predict that as these bodies approach the Sun, their volatile ices vaporize, releasing gas and dust that form characteristic Comet tails, following patterns confirmed through centuries of cometary observation. On the other hand, if these objects are something more exotic, perhaps constructed from materials or processes unknown to current science, deviations from the expected behavior should become evident during their nearest encounters with the Sun. These anomalies might manifest as unexpected brightening, unusual tail structures, or erratic activity patterns that do not conform to natural sublimation models. However, a significant challenge complicates this investigative effort. The same solar glare that makes perihelion such a scientifically rich phase also renders the objects difficult or impossible to observe from Earth-based telescopes during their closest approach. During these critical moments, the bodies will be concealed behind the sun's blazing disk, leaving astronomers to infer their state and activity only from the data available when they re-emerge into view, if they reappear at all. This creates a substantial observational gap, a window in which direct measurements are impossible, and speculation can thrive unchecked. In such circumstances, the absence of direct data leaves room for a multitude of interpretations. Without concrete observations, any theory, whether natural or artificial, can be constructed and considered plausible. This vacuum of evidence fosters a fertile environment for hypothesis proliferation, often influenced by human psychology and cultural biases. The silence during October might reveal as much about our collective psyche, our hopes, fears, and the desire for extraordinary explanations, as it does about the true nature of these cosmic visitors. Regardless of which hypothesis eventually withstands scrutiny, the upcoming planetary approaches mark a moment of genuine scientific significance, whether these objects are merely exotic ice fragments or something far stranger. Their passage offers a rare chance to expand our understanding of what exists in the often invisible spaces between stars, and what might occasionally drift into our solar neighborhood. The narratives we craft around them, be they about alien technology, natural phenomena, or cosmic coincidences, reflect as much about human hopes and fears as they do about the objects themselves. Perhaps it is fitting that our curiosity shapes these stories, echoing age-old questions. Is it a simple comet, a fortress-like construct, or the long silent reply to a message we never knew we sent? Part 6. The Discovery and Path of 3I Atlas. The story of the interstellar object known as 3I Atlas begins with a seemingly insignificant event, a single pixel's brightness flickering on a CCD detector in the stark, high-altitude deserts of northern Chile. This small change, barely noticeable in the vast expanse of the night sky, marked the moment when this cosmic wanderer first revealed itself as more than just a faint point of light. It was July the 1st, 2025, a date that would go down in history as the day humanity's automated sky surveys finally detected an object from beyond the bounds of our solar system. The Atlas survey, formerly called the Asteroid Terrestrial Impact Last Alert System, operates a network of 4 robotic telescopes strategically positioned across 2 different continents. These instruments are primarily designed for a vital purpose: the early detection of potentially hazardous asteroids, space rocks on trajectories that might threaten Earth. Their systematic scans of the sky are meticulous, comparing each night's observations against comprehensive catalogs of known celestial objects. When they detect something new, a star-like point that moves, brightens, or appears where previously there was nothing, these telescopes automatically record and analyze the data, seeking to determine the object's trajectory and nature. In this case, the faint point of light captured. When the Atlas telescope at Rio Hurtado first detected the object now known as 3I Atlas, it appeared merely as a faint, indistinct smudge against the backdrop of countless distant stars. Its subtle glow and slow movement offered no immediate indication of its true nature. Yet, as is often the case in astronomy, motion and the way objects traverse space tell a deeper story, one that can only be unraveled through careful analysis and precise calculations. Within mere hours of its initial sighting, orbital computations revealed something remarkable. This newcomer was not a typical solar system object, but something extraordinary, The calculation showed that 3I Atlas was on a hyperbolic trajectory, an unmistakable sign that it was unbound from the sun's gravitational influence. In the language of orbital mechanics, celestial objects are classified into two broad categories. The first encompasses those that belong to our solar system, following elliptical paths that eventually loop back, returning to their point of origin after completing their journeys around the sun. The second category includes objects that are passing through, traveling along hyperbolic paths that carry them past the sun only once before they continue outward, vanishing into the vastness of interstellar space forever. By this measure, 3I Atlas falls squarely into the latter group. Its hyperbolic orbit confirms its status as only the third confirmed interstellar visitor in recorded human history, a rare and valuable glimpse into objects originating from beyond our cosmic neighborhood. The very nature of its trajectory offers a narrative, a story of a voyage that originated in the dark, silent depths between stars, far outside the bounds of our solar system. Examining the specifics of its path, scientists noted that the trajectory carried an inclination of approximately 175 degrees relative to the plane in which Earth and the other planets orbit the Sun. In practical terms, this means Atlas approached our solar system from beneath the ecliptic plane, traveling in a retrograde direction, opposite to the usual orbital motion of the planets. Such an approach is a hallmark of objects formed elsewhere in a different stellar environment, shaped by processes and conditions not familiar to our local star's formation history. The discovery timeline underscores how perilously close we came to missing this visitor altogether. Interstellar objects do not follow predictable orbits within our solar system. Instead, they arrive from random directions, often spending months or even years traversing regions of space that place them perilously close to the sun from our perspective. Their approach is often cloaked in the glare and brightness of the sun, making detection difficult until they venture into the more observable regions of space near Earth's vicinity. By the time Atlas was finally identified, it had already slipped through the outer reaches of our solar system, beginning its final rapid approach toward perihelion, the closest point to the sun in its orbit. Backtracking its path suggests that this wanderer had been within our cosmic neighborhood since early 2025, possibly as early as late 2024. Throughout this time, it was gradually brightening, its surface activity increasing as the sun's warmth began to animate its icy interior, producing the first signs of a cometary tail in gaseous coma. This delayed discovery highlights one of the fundamental challenges inherent in detecting interstellar objects. We can only observe them clearly once they become sufficiently bright and favorably positioned relative to Earth. Their initial approach is often too faint or obscured by solar glare, meaning we tend to catch these visitors only in their later, more conspicuous phases. Current projections place 3I Atlas's perihelion, its closest approach to the sun, around the 29th or 30th of October in the year 2025. During this critical phase, it will pass at a distance of approximately 1.35 to 1.4 astronomical units. To put that into perspective, this places the object just inside the orbit of Mars, making it closer to the sun than any other interstellar visitor observed before. Its trajectory will carry it past Mars itself on the 3rd of October at a distance roughly 30 million kilometers away. While this may seem like a vast distance from a human standpoint, it is close enough for the advanced instruments aboard Martian spacecraft to potentially observe and analyze the object during this pivotal moment in its journey. The European Space Agency has outlined preliminary plans to leverage Mars orbiting spacecraft for opportunistic observations during this critical encounter. These assets, designed primarily for planetary and atmospheric studies, will be employed to gather valuable data on the approaching interstellar visitor, capitalizing on the unique vantage points provided by Mars's orbital infrastructure. Meanwhile, for observers on Earth, the interstellar object designated 3I Atlas will maintain a safe and respectful distance throughout its passage through our solar system. Its closest approach to Earth is projected to occur at approximately 1.8 astronomical units, about 270 million kilometers away. This considerable distance guarantees that the visitor poses no threat to our planet, while still remaining within the observational reach of our most advanced telescopes during periods of optimal viewing conditions. Current size estimates for 3I Atlas remain inherently uncertain, primarily due to the difficulties in observing such faint and distant objects. However, data gathered from the Hubble Space Telescope on the 21st of July 2025 constrains the nucleus's diameter to perhaps a few kilometers. This scale appears sufficient to produce the cometary activity observed, such as the expanding coma and tail. Yet it is notably smaller than many of the spectacular comets that have dazzled our skies in recent decades. Nonetheless, these size estimates carry significant uncertainties, reflecting the inherent challenges of remote sensing at such vast distances. The brightness we perceive from Earth is primarily the result of sunlight scattering off dust and gas in the coma surrounding the nucleus, rather than the nucleus's own luminosity. Accurately determining the nucleus's true size involves detailed modeling of how efficiently it reflects sunlight, as well as understanding the rate at which it releases material into space through sublimation. These sublimation processes, where ices transform directly from solid to gas, play a crucial role in shaping the observable features of the comet and in estimating its physical dimensions. The coordinated observational campaign surrounding 3I Atlas represents one of the most comprehensive and intensive studies ever conducted of an interstellar visitor. The high-resolution imagery provided by the Hubble Space Telescope has been instrumental in tracking how the structure and brightness of the coma evolve over time, revealing subtle changes in the activity and composition of the object. Complementing this, the James Webb Space Telescope, utilizing its infrared capabilities, turned its sensors toward the comet in August. These infrared observations have unveiled intricate details about its chemical makeup, information that remains inaccessible to ground-based telescopes due to atmospheric interference. In addition, the Very Large Telescope situated in Chile has contributed crucial spectroscopic data, breaking down the visitor's light into its constituent colors. This spectral analysis enables scientists to identify specific molecules and atoms glowing within the coma, providing vital insights into its composition. The data reveals some extraordinary chemical signatures, notably strong nickel emission lines without accompanying iron signals, prominent cyanogen lines, and a dominance of carbon dioxide, characteristics that have elevated 3I Atlas to a subject of intense scientific scrutiny and public fascination alike. As the object continues its approach toward the October encounters, multiple space telescopes remain actively engaged in tracking and analyzing this visitor. However, time is rapidly running out for comprehensive observations from Earth's vantage point. Increasingly unfavorable geometric conditions, such as the object's growing distance and the solar elongation angles, will soon render ground-based observations impossible. During this critical window, the bulk of the scientific effort will depend on data collected by Mars-based assets during the brief flyby, highlighting the importance of international coordination and collaboration in modern astronomy. This global effort illustrates how interconnected and collaborative contemporary astronomical research has become. Telescopes across different regions, beginning with those in Chile during the hemisphere's night, then transitioning to facilities in Hawaii and the Canary Islands, are working in tandem. As Earth rotates, the observational coverage shifts seamlessly from one zone to another, ensuring continuous monitoring. This coordinated approach maximizes the scientific return, capturing as much data as possible before the object recedes beyond reach. and underscores how modern astronomy relies on international cooperation to unlock the secrets of distant cosmic visitors. Space-based observatories offer an invaluable advantage. They maintain continuous oversight across day-night cycles and can peer through atmospheric conditions that often hinder ground-based telescopes. This persistent vigilance becomes especially crucial when tracking faint or distant objects that might otherwise slip through our observational grasp. Yet perhaps the most compelling aspect of the discovery of 3I Atlas lies in what we nearly overlooked entirely. The faintness of this interstellar visitor, coupled with its initially unfavorable viewing geometry, meant that for months, possibly even years, it silently traversed our solar system largely undetected. This raises a profound question. Just how many such objects have we missed? It's conceivable that countless other cosmic wanderers have passed through our neighborhood without ever becoming bright enough or aligned favorably enough to be caught by our surveys. The efficiency of detection for interstellar objects hinges heavily on several factors, primarily their size, their composition, and the specific trajectories they follow through space. Smaller bodies or those lacking substantial comas might remain invisible until they venture very close to the sun, where solar heating can trigger activity. Similarly, visitors approaching from particular directions could be concealed in the overwhelming glare of the sun for their entire passage through the inner solar system, effectively cloaked from our instruments. Statistical models support this unsettling possibility. For each interstellar object we successfully detect, dozens or even hundreds may pass by unseen. 3I Atlas, therefore, is not merely a solitary discovery, it's a window into a much larger, largely unrecognized population of cosmic travelers that regularly cross our region of space. As October of the year 2025 unfolds, this particular visitor continues its unwavering journey towards perihelion, the closest point to the sun in its orbit, and it is now within reach of even modest telescopic equipment. Its distinctive green-tinged coma has become a striking feature in the autumn sky, serving as a poignant reminder that our solar system functions as a crossroads for travelers originating from distant stars. Before this enigmatic visitor vanishes into the blinding glare of the sun, Mars stands ready to witness whatever secrets it might be concealing. The question that persists is whether our current instruments, both those orbiting the red planet and those here on Earth, are advanced enough to distinguish between the truly exotic and the merely extraordinary. In this fleeting window of opportunity, with time rapidly running out, the challenge remains to discern the nature of this remarkable cosmic wanderer before it disappears from our view completely. Turning now to the realm of chemistry and color, Part 7 in this unfolding story. The universe communicates largely through wavelengths of light, and 3I Atlas has been painting its story in vivid green since its discovery. As it approaches our sun, the comet's nucleus begins to heat up, releasing gases that had been locked away in ice for millions of years, sublimating into space. However, the palette that emerges from this cosmic painter defies expectations rooted in our knowledge of objects formed within our solar neighborhood. The striking green coloration that has captivated both astronomers and observers worldwide originates from a complex interplay of chemical reactions and physical processes occurring in the near-vacuum environment surrounding the comet's nucleus. When molecules in the comet's coma are excited by solar ultraviolet radiation or collide with energetic particles, they emit light at highly specific wavelengths, spectral fingerprints that are dictated by the quantum mechanical properties of their electron orbitals. For green emission, the primary culprits tend to be diatomic carbon molecules, C2, and radicals such as cyanogen, Cn, both of which fluoresce with a brilliant green glow when illuminated by sunlight. This luminescence is not merely a visual spectacle, but a vivid indicator of the chemical makeup and physical conditions prevailing in the comet's environment, offering a glimpse into its origins and the processes that have shaped it over eons. Coverage by Live Science has delved into the intriguing phenomena surrounding the greenish luminescence observed in this interstellar visitor, with scientists proposing various candidate molecules that could be responsible for its distinctive hue. While diatomic carbon has long been considered the most probable explanation, drawing on prior cometary studies and spectral signatures, definitive identification through high-resolution spectroscopy remains elusive. This distinction is not merely academic. It holds profound implications because different molecules carry unique stories about the environmental conditions and chemical pathways that shaped this object in its distant stellar nursery. Cyanogen, a molecule composed of carbon and nitrogen atoms, stands out as one of the most toxic substances known to chemistry. Despite its deadly reputation, cyanogen can emit a stunning ethereal glow when it is liberated into the vacuum of space. Its presence in the spectral data of comets offers valuable clues about the organic chemistry that transpired billions of years ago, deep within the stellar cloud where this comet, designated 3I Atlas, was born. By examining the relative abundance of cyanogen compared to other carbon-based molecules, researchers can infer details about the temperature, pressure, and chemical processes that existed in the star-forming environment of its origin. Such information provides a window into the conditions of an ancient stellar nursery, revealing the molecular fingerprint of a bygone era. However, the green glow that initially captivated astronomers is only the most visible aspect of a far more complex and nuanced chemical narrative. When the Very Large Telescope in Chile turned its formidable spectrographs toward 3I Atlas during its approach, the resulting molecular fingerprints challenged prevailing understandings of how interstellar objects should behave chemically. In particular, the detection of prominent emission lines from nickel, notably at a wavelength of 0.77 nanometers, manifesting as a vivid green, presented a perplexing puzzle. These nickel emissions appeared strongly and distinctly against the background spectrum typically associated with cometary activity. What made this even more puzzling was the absence of the expected signatures of iron, which usually accompanies nickel in natural cosmic environments. In most meteorites and celestial samples, nickel and iron are found together in ratios that mirror the nuclear processes that forged them within stellar cores, ratios that are remarkably consistent across the cosmos. The periodic table's abundance pattern suggests that wherever these elements are present, they should appear in predictable, near-equal proportions. Yet 3I Atlas seemed to defy this fundamental rule, displaying a strong nickel signal without any corresponding iron emission. The implications of this anomaly are significant, prompting scientists to reconsider their assumptions about the composition and history of such objects. Several hypotheses have been proposed to explain this unexpected chemical profile. One possibility is that the comet's surface contains nickel-bearing organic compounds, which are stable in the cold, frigid environment of interstellar space. Under the influence of solar heating during its approach, these compounds might decompose selectively, releasing nickel atoms into the gas phase while leaving iron behind. Additionally, processes related to space weathering, gradual chemical and physical alterations occurring over millions of years, could have modified the surface chemistry of the comet. Such alterations might influence how different elements are incorporated into sublimating ices, further skewing the elemental ratios observed in the gas and dust released during the comet's approach. These processes could involve complex interactions with cosmic radiation, micrometeorite impacts, or thermal cycling, all of which could preferentially favor the release of nickel over iron. In essence, the chemical story written in the spectra of 3I Atlas is a testament to its unique and possibly extraordinary history, one that challenges straightforward expectations based on well-established cosmic abundance patterns. as scientists continue to analyze the spectral data. The puzzle of this comet's unusual nickel signature remains a compelling mystery, hinting at a formation environment and evolutionary path that may be fundamentally different from the typical bodies born within our own solar system. The comprehensive chemical profile assembled through numerous observational efforts portrays 3I Atlas as a visitor whose origins and formation circumstances are markedly different from those of objects born within our own solar system. Notably, recent findings from the James Webb Space Telescope, utilizing its highly sensitive NIRSPEC instrument, have uncovered a composition predominantly rich in carbon dioxide. Interestingly, water vapor, the molecule often associated with cometary activity, appears surprisingly scarce during the initial phases of this comet's activity. This dominance of carbon dioxide narrates a tale of formation in a markedly colder, more volatile-rich environment, contrasting sharply with the warmer regions where Earth and the terrestrial planets originated. Different stellar systems experience distinct temperature and chemical profiles during planet formation, which can lead to comets with unique compositions that deviate significantly from those typically observed in our own Kuiper Belt or Oort cloud populations. Further analysis by the European Space Agency's infrared observations has emphasized that the low ratio of water to carbon dioxide detected at large heliocentric distances is characteristic of what researchers refer to as early activation behavior. In this phase, the most volatile ices, such as carbon dioxide, sublimate first as the comet begins its inward journey toward the Sun, initiating its observable activity. As 3I Atlas advances closer to perihelion, the point of closest approach to the Sun, it is expected that the contribution of water vapor to its overall gas output will increase. This is because less volatile ices, such as water, reach their sublimation temperatures at these shorter distances. Monitoring the production rates of various molecular species thus offers a valuable window into the intrinsic nature of this celestial visitor. In fact, as 3I Atlas approaches the Sun, the rates at which it emits water vapor, carbon dioxide, cyanogen, and other molecules increase in a predictable fashion, correlating with the decreasing heliocentric distance. These production curves align well with established models of sublimating ices, strongly indicating that the behaviors we are witnessing are rooted in natural physical processes rather than artificial emissions. Nevertheless, despite these expected patterns, subtle anomalies continue to pique scientific curiosity. The ratios between different molecular production rates do not perfectly match the predictions derived from models based on familiar solar system comets. Similarly, the brightness variations observed over time exhibit irregularities that could suggest either inhomogeneities across the nucleus's surface, meaning differing compositions or activity levels in various regions, or episodic outgassing events triggered by subsurface processes that remain poorly understood and difficult to predict. The role of the amateur astronomy community has been instrumental in documenting these chemical and physical changes over the course of the comet's approach. High-quality imaging from experienced observers worldwide provides a level of temporal detail and coverage that surpasses what professional telescopes, often limited by time constraints and competing priorities, can achieve. These observations have been crucial in tracking evolving features such as coma coloration, tail morphology, and overall brightness, thus complementing the detailed spectroscopic studies conducted by major observatories. However, the dissemination of preliminary findings through social media has, at times, amplified certain aspects of these chemical mysteries beyond what the data substantively support. Notably, the reported observation of nickel signatures in the absence of iron has been interpreted by some as potential evidence of industrial processes or manufactured signatures, an idea that, despite the allure of the hypothesis, remains speculative. Natural explanations such as unusual surface chemistry or selective sublimation processes are available and more consistent with current understanding. These developments highlight the importance of cautious interpretation and rigorous scientific validation amid the excitement of early discoveries. NASA maintains a cautious yet measured stance regarding the intriguing visitor known as 3I Atlas. The agency's official position underscores that the current observational data aligns with what one would expect from a natural cometary object, albeit one exhibiting characteristics that are unusual, yet not entirely unprecedented, within our understanding of such bodies. Scientists at NASA point out that these chemical peculiarities are in fact anticipated for objects originating around other stars. Different formation environments, marked by variations in temperature, pressure, and elemental abundances, can give rise to compositions that diverge significantly from the familiar makeup of comets and asteroids formed within our own solar system. This distinction between what can be classified as exotic and what is extraordinary proves to be a vital interpretative tool in analyzing these cosmic phenomena. Exotic chemistry refers to unusual yet physically explainable chemical signatures that arise from known processes that we understand well enough to reconcile with natural origins. On the other hand, extraordinary chemistry suggests features that, while perhaps initially puzzling, could point toward artificial origins or some form of engineered modification, thus crossing a line that challenges our current scientific paradigms. In the case of 3I Atlas, the evidence indicates the display of exotic characteristics. The question that persists among scientists, however, is whether these traits are simply exotic enough within natural frameworks, or if they have advanced beyond that, hinting at something more extraordinary, possibly artificial, yet remain under active debate within the scientific community. To better contextualize these anomalies, it is instructive to look back at the history of interstellar visitors, such as Comet Borisov. This earlier object, which was scrutinized in detail, also exhibited curious chemical features that at first bewildered researchers. Notably, Borisov's ratio of carbon monoxide to water differed markedly from the typical compositions seen in comets originating from our solar system. Yet subsequent detailed analysis suggested that these differences could be explained by formation in the colder outer regions of its parent stellar system, regions with conditions that favor the retention of more volatile compounds like carbon monoxide. Further insights into the chemical makeup of 3I Atlas come from observations conducted with the Very Large Telescope, VLT. These analyses include discussions of alternative chemical pathways that could produce the observed signatures, particularly the nickel emissions, without resorting to notions of exotic or artificial origins. One plausible explanation is that nickel carbonyl compounds, complex molecules formed through reactions between nickel-bearing dust grains and carbon monoxide in the cold interstellar medium, could account for the preferential release of nickel over iron when the comet is heated by solar radiation. This process, rooted in known chemistry, offers a natural explanation for the observed spectral signatures. As October of 2025 advances and as 3I Atlas draws nearer to its perihelion, the closest point to the Sun, opportunities for detailed chemical analysis are rapidly diminishing. The same solar heating that activates the more intriguing chemical processes in the comet's coma also places the object at increasingly challenging viewing angles from Earth-based telescopes. The geometry of the situation means that, as the comet approaches perihelion, our vantage point becomes less favorable for capturing high-resolution data, and the window for detailed observation narrows. This raises a provocative question. What if the changes we observe are not merely the result of natural chemical activation under solar influence? Could there be an underlying protocol, a set of programmed responses that is activating within the molecules themselves? Perhaps according to some deeper, deliberate design? The molecules governed by the laws of quantum mechanics emit light with a precision that, to our current understanding, is entirely natural. Yet their ultimate origins, whether from a natural stellar nursery or an artificial construct, remain concealed behind the language of quantum physics. They glow, not revealing their true purpose, merely obeying the fundamental rules dictating their behavior. Rules that we have yet to fully decipher in the context of potential extraterrestrial engineering. On the horizon of October, the upcoming Mars flyby scheduled for the third day of that month promises to be a pivotal event. The celestial rendezvous has been millennia in the making. On this date, 3I Atlas is expected to pass by Mars at an approximate distance of 30 million kilometers, a span that, in the grand scale of interstellar travel, is relatively modest. For perspective, this distance is about 5 times the separation between Earth and the Moon, or roughly 1/5 of an astronomical unit. Although this might seem distant in human terms, in the context of interstellar objects following hyperbolic trajectories at speeds that can reach tens of kilometers per second, this is a significant opportunity for close-range observation. The Red Planet's robotic explorers, its fleet of orbiters and landers, will be poised to turn their instruments toward this visitor. With their advanced sensors, spectrometers, and high-resolution cameras, they stand ready to gather data at levels of detail that could reveal the composition, structure, and activity of an object from another star system, making this perhaps the most comprehensive observational opportunity we will have for such an interstellar visitor. The distance in question is approximately 5 times the space separating Earth from the Moon, or roughly 1/5 of an entire astronomical unit. While this may sound modest in cosmic terms, it becomes remarkably significant when considering interstellar visitors hurtling through space along hyperbolic paths at tens of kilometers per second. At such velocities, even a relatively small window of proximity offers an extraordinary chance for detailed scientific examination during a critical phase of the comet's journey as it nears the Sun. Recognizing the importance of this fleeting opportunity, the European Space Agency has already outlined preliminary plans to orchestrate a coordinated observational campaign involving multiple spacecraft orbiting Mars. This approach aims to maximize data collection within a narrow, carefully chosen time frame. Among these, the ExoMars Trace Gas Orbiter, originally designed to analyze the Martian atmosphere, carries a suite of spectrometers capable of dissecting the chemical makeup of the expanding coma of the comet, officially designated as 3I Atlas. These instruments can identify and quantify the various molecules released as the comet warms and begins to outgas, providing vital insights into its composition and activity. Complementing this effort, Mars Express, now in its 3rd decade orbiting the Red Planet, offers additional imaging and spectroscopic capabilities. Its suite of instruments can capture high-resolution images and spectral data, contributing further to our understanding of this extraordinary cosmic visitor. Even more promising is NASA's Mars Reconnaissance Orbiter, equipped with the highly sensitive high-resolution imaging science experiment, HiRISE, camera system. Although the comet will be too distant for surface feature resolution, meaning we won't be able to see fine details like surface craters or geological features, the exceptional sensitivity and resolution of HiRISE could nonetheless reveal intricate details about the coma's structure, dust distribution, and the shape and orientation of the tail. These are features that remain virtually invisible to Earth-based telescopes, owing to atmospheric distortion and limited resolution. The unique vantage point provided during the Mars flyby offers several advantages that terrestrial observers simply cannot match. As Mars moves into a different position relative to the Sun and the comet's trajectory, it can reveal aspects of the coma and tail structure that are hidden from ground-based perspectives. Without Earth's atmosphere to cause seeing limitations or absorb certain wavelengths of light, images captured from Mars can be sharper, and photometric measurements, those that determine brightness and color, can be more precise. This may allow scientists to analyze the dust and gas in unprecedented detail, tracking how the coma develops and responds to the sun's heating. However, implementing this observational strategy is not without challenges. Mars orbiters were primarily engineered for planetary science, studying Mars's surface, atmosphere, and magnetosphere, and their systems are not optimized for tracking distant, fast-moving objects in deep space. Their pointing mechanisms, communication protocols, and onboard data storage are tailored for planetary observations, requiring meticulous planning to redirect their instruments toward the comet, which is millions of kilometers away. This must be balanced carefully with their primary mission objectives, ensuring that their scientific and operational priorities are maintained. The primary goals of these Mars-based observations are to investigate aspects of 3I Atlas that are poorly understood from Earth. High-resolution imaging could shed light on the size distribution of dust particles in the coma, achieved by analyzing how these particles scatter sunlight at different angles, revealing details about their composition and the physical processes at play. Spectroscopic measurements can help constrain the relative abundances of various molecular species released during active outgassing as the comet approaches the Sun. Information essential for understanding its origin and evolution. In addition, ion tail geometry presents another promising target. The ion tail, shaped by interactions between the solar wind and the comet's charged particles, can reveal much about the activity level and the environment surrounding the comet. Observing how the tail aligns and changes from this vantage point could provide clues about the magnetic and electric conditions in the local space around the comet, further enriching our understanding of its behavior as it makes its closest approach. The dynamic interplay between the solar wind and the ionized gases within a comet's coma gives rise to striking tail structures that unmistakably align with the orientation of the local magnetic field. This natural phenomenon offers a unique opportunity for detailed study, especially when viewed from Mars's distinctive vantage point. From this proximity, scientists may glean insights into the comet's gas production rates and the characteristics of the surrounding space environment, details that would remain obscured or impossible to observe from Earth's distant telescopes. The timing of this encounter with Mars elevates the urgency and importance of these observational plans. As the comet, designated 3 Atlas, approaches its perihelion in late October, it is expected to experience increasingly intense solar heating. This process could trigger its most vigorous outgassing activity during its passage through our solar system, an event that might not recur for decades or even centuries. The upcoming Mars flyby coincides precisely as this activity escalates, providing a fleeting window into the physics of cometary behavior at its peak. Such an opportunity is invaluable, yet it is tempered by practical limitations inherent in current technological capabilities. Given that the comet will be approximately 30 million kilometers away from the orbiting spacecraft, it will appear to most instruments as little more than a faint point of light, a distant speck rather than a detailed object. This distance significantly constrains the ability of Mars-based instruments to resolve the nucleus's finer structures or to construct detailed maps of the coma and tail with the clarity achieved in dedicated Earth-based observations. Adding to these challenges are the communication delays stemming from the vast interplanetary distance. Radio signals take between 4 and 24 minutes to traverse the space between Earth and Mars, depending on their relative positions in their orbits. This latency necessitates that observation sequences and commands be prepared well in advance, uploaded to the spacecraft's onboard memory, and executed without real-time adjustments. Any unanticipated changes in the comet's activity or unexpected phenomena must therefore be anticipated and programmed ahead of the flyby, limiting flexibility in response to evolving conditions. Further complicating the observational efforts are the unpredictable weather patterns on Mars. Dust storms, whether global or localized, pose a significant wildcard. While large-scale dust storms are infrequent, regional dust activity can temporarily obscure the sky, diminish visibility, and contaminate the sensitive instruments aboard the orbiters. Mission planners must carefully weigh the timing of observations, striving to maximize data collection during clear conditions while accommodating the inherent unpredictability of Martian weather. The logistics of data collection and transmission add another layer of complexity. Data gathered by Mars orbiters during the flyby must then be transmitted back to Earth during scheduled communication windows. These windows often do not align perfectly with the brief and critical moments of the comet's closest approach. Consequently, some of the most scientifically valuable observations, such as detailed morphological studies of the nucleus or high-resolution coma imagery, may only be available days or even weeks after the event. This delay hampers timely follow-up analyses and limits the capacity for immediate sharing or collaborative interpretation within the global astronomical community. Despite these hurdles, the Mars flyby remains our most promising opportunity to examine an interstellar visitor during its most active phase. Earth-based telescopes will soon lose sight of 3 Atlas as it sinks into the Sun's glare, making the observations from Mars potentially the last high-quality glimpse we have of the object until it re-emerges months later, if at all. This window provides an unparalleled chance to test competing theories about the nature of the comet, whether it is a pristine interstellar relic or a more familiar solar system-bound body exhibiting unusual activity. The data collected could be crucial in advancing our understanding of such objects, offering insights into their composition, behavior, and the processes driving their outgassing during proximity to the Sun. In the realm of cometary science, the behavior of natural objects passing close to the Sun follows well-understood patterns. As these icy bodies approach the star, they undergo thermal processing, an intense heating that causes their frozen volatiles to sublimate, releasing dust and gas into space. This activity manifests in predictable ways, such as gradual increases in the brightness of their surrounding coma and the development of tails that stretch away from the Sun, shaped by solar wind and radiation pressure. By carefully monitoring these changes, specifically variations in the luminosity of the coma and the morphology of the tail, scientists can infer the composition and physical state of these comets and how they respond to solar heating. Any significant deviation from these anticipated patterns might hint at something more unusual or even exotic about the visitor's nature, prompting researchers to consider alternative explanations beyond standard cometary physics. However, it is crucial to maintain realistic expectations about what these observations can reveal. The upcoming flyby near Mars will not involve any physical contact or close approach, as the visitor will remain millions of kilometers away throughout the encounter. No direct sampling will be conducted, and surface features or internal structures cannot be resolved with current instrumentation. The spacecraft orbiting Mars will serve primarily as observational platforms, aimed at gathering data remotely rather than physically interacting with the object. This mission also functions as a proof of concept for future studies of interstellar visitors. The techniques refined during the Mars flyby will help shape more sophisticated observation strategies for subsequent encounters. These methods may include coordinated efforts across multiple international agencies, employing advanced spectroscopy, high-resolution imaging, and real-time data sharing, all aimed at unraveling the secrets of these rare cosmic wanderers. Contingency planning remains a vital aspect of the mission strategy. Recognizing that technical failures, communication disruptions, or unfavorable viewing geometries could limit or entirely prevent data collection during the critical moments of the flyby. Backup observation plans are in place. Ground-based telescopes, despite their limitations, will provide some redundancy, though their efficacy diminishes as the sun's glare intensifies and atmospheric interference increases closer to the time of closest approach. The timeline of the Martian encounter condenses the most scientifically valuable observation window into just a few hours or days around the moment of perihelion, when the comet is at its closest point to the sun. During this brief but intense period, our robotic emissaries orbiting Mars will turn their instruments toward the visitor, attempting to capture any signals, emissions, or features that might reveal its nature. If Mars could somehow eavesdrop on the electromagnetic spectrum during those critical hours, what stories might it intercept amidst the vast static of space? The instruments will operate with robotic patience, paired with the curiosity of human ingenuity, aiming to decode any messages encoded in the light emitted or reflected by this star-bound traveler. But before any data collection begins, the visitor must pass through its cosmic appointment with our solar system's fourth planet, Mars. Carrying whatever mysteries and clues it holds, it will traverse the final stretch of space, passing beyond the watchful eyes of our Martian sentinels toward its ultimate destination, hidden behind the dazzling glare of our star, the Sun. This brings us to the next chapter, Part 9. Dedicated to what we'll call Swan R2, the new giant emerging from the depths of our own solar system. While the interstellar visitor, designated 3I Atlas, captured widespread attention as an exotic object from beyond our solar borders, another comet was quietly, yet spectacularly, preparing to steal the show. Known as Comet C/2025 R2, or simply Swan R2 after its discovery and data from solar and heliospheric observatories, this object has evolved into one of the most breathtaking cometary displays seen from Earth in recent years. The story of Swan R2 begins with the meticulous dedication of an amateur astronomer named Vladimir Basugli. For hours, Vladimir scoured images from specialized instruments, searching for telltale signs of a new comet lurking amidst the solar glare. His patience paid off on September 11, 2025, when he noticed an anomalous brightening, an indication that something unusual was unfolding in the solar system's inner regions. This faint glow, initially hidden in the overwhelming brightness of the sun's proximity, marked the beginning of a discovery that would soon captivate both the scientific community and the public alike. On the significant date of September 11th, in the year 2025, the patient dedication of Vladimir Basugli finally bore fruit. His unwavering attention to the subtle signals within the solar wind data led to the discovery of an unusual brightening, a telltale sign that would soon be confirmed as a previously unknown comet making its approach toward the sun. This discovery was remarkable not only because of the comet itself, but also because it was detected through an unconventional method. The Swan instrument aboard the SOHO spacecraft, which is primarily designed to study the solar wind's interaction with the interplanetary environment. Despite its original purpose, Swan's ability to map the distribution of hydrogen atoms, produced when water molecules are broken apart by intense solar ultraviolet radiation, enabled it to detect cometary activity that often remains hidden from traditional telescopic observations. This method is especially valuable for objects lurking perilously close to the sun, where ground-based telescopes cannot safely observe them due to the overwhelming glare. The emergence of Swan R2 from solar conjunction exemplifies one of the most fundamental and persistent challenges in the discovery of comets: their long, often unpredictable journeys from the distant edges of our solar system. These objects, traveling along elongated, sometimes highly eccentric orbits, can spend months or even years approaching the sun from directions that place them at very small, angular separations from our star as seen from Earth. Such approaches are difficult to observe directly because of the sun's brightness and the limitations of terrestrial telescopes. This phenomenon, known as the hole-at-check effect, named after the Austrian astronomer Ernst Öpik, who first described similar observational biases, explains why many spectacular comets seem to appear suddenly, fully formed, active, and brilliant, emerging out of the solar glare with little warning. The comet was officially designated as C-2025 R2, following the naming convention set by the International Astronomical Union. The initial C indicates that it is a long-period comet, likely originating from the distant Oort cloud, a vast icy reservoir surrounding our solar system. The year 2025 signifies its discovery date, while the R2 denotes that it was the second comet discovered in the latter half of September. By mid-September of that year, Swan R2 had already reached a brightness visible to the naked eye for observers in dark sky environments, shining at approximately 6th magnitude, a threshold at which celestial objects can be seen without optical aid under ideal conditions. Unlike many comets that reach a peak brightness and then gradually fade, Swan R2 defied expectations by continuing to brighten as it emerged from its solar encounter. Its brightness increased steadily, and the comet's tail, an elongated streamer of dust and gas, began to develop spectacularly, capturing the attention of astrophotographers around the world. This rapid development was highlighted in the astronomy picture of the day on September 16th, which featured Swan R2 as a newly discovered visitor visible through binoculars. Observers noted its swift brightening and the impressive tail that stretched across the sky, becoming a favorite target for astronomers and skywatchers alike. Positioned near the bright star Spica in the constellation Virgo, the comet offered a convenient reference point for amateur astronomers attempting to locate it during twilight hours. Observational reports soon poured in, describing a tail extending up to 2 degrees across the sky, about 4 times the apparent diameter of the full moon, an indication of a structure spanning millions of kilometers in physical space. Although these measurements were approximate, owing to the subjective nature of visual observations and the limitations of digital imaging techniques, they vividly conveyed the comet's impressive size and activity. The orbital characteristics of Swan R2 narrate the story of an interstellar visitor, one likely originating from the distant outskirts of our own solar system. Its trajectory, shape, and speed suggest that this comet has traveled vast interstellar distances before arriving in our neighborhood, offering scientists a rare glimpse into the composition and dynamics of objects from beyond our familiar planetary realm. In stark contrast to 3I Atlas, which follows a hyperbolic interstellar trajectory, Swan R2 traces a vastly different path through our solar system, a highly elongated elliptical orbit that stretches from the icy, frigid reaches beyond Neptune's distant orbit to a point within just half an astronomical unit from the Sun. This journey, spanning many decades or even centuries, kept the comet in a state of dormancy, its surface frozen and inert for most of its voyage. It was only when solar radiation gradually heated its surface that Swan R2 began to display the spectacular activity observed today. The moment of perihelion, the closest approach to the Sun, occurred on September the 12th, 2025, when the comet reached its perihelion point at roughly half the distance between Earth and the Sun, approximately 0.5 astronomical units. This proximity subjected Swan R2 to intense solar heating, vaporizing surface ice and unleashing a flurry of dust and gas that formed the luminous coma and the sweeping tail structures so characteristic of active comets. Looking ahead, Swan R2's closest encounter with Earth is projected for October the 21st, 2025, when it will pass within approximately 0.27 astronomical units, about 40 million kilometers, from our planet. This favorable geometric alignment offers an excellent opportunity for detailed observation, as the comet will be at its most accessible in our night sky during this period. Coincidentally, this is also when 3I Atlas completes its own perihelion approach, marking a rare convergence of two significant celestial visitors. During mid-September, current brightness estimates place Swan R2 at about magnitude 6 to 7, making it readily visible through binoculars and beginning to approach naked-eye visibility under optimal conditions. Its continued brightening hints that it could reach magnitude 4 or 5 by the time of its closest approach to Earth, potentially ranking as one of the brightest comets visible in the year 2025. The Southern Hemisphere will enjoy the most favorable conditions for viewing Swan R2 during its evening apparition, with the comet prominently positioned low in the western sky after sunset. Meanwhile, observers in the Northern Hemisphere can still catch glimpses of the comet as it drifts along the horizon, offering a fleeting yet spectacular sight. The comet's apparent position relative to the ecliptic plane and its motion against Earth's backdrop result in changing viewing geometries throughout its visibility window, alterations that influence how and when it can be best observed. Across the globe, amateur astronomers and dedicated networks have mobilized in unison, diligently tracking Swan R2's development and contributing to a dynamic real-time database of observations that complements the efforts of professional astronomers. High-quality imagery captured by experienced comet photographers reveals intricate details within its tail, including potential disconnection events, phenomena where magnetic field interactions temporarily sever portions of the tail, especially the iron-rich segment, from the main body of the comet. Yet despite these advancements, significant uncertainties linger in Swan R2's orbital parameters. The relatively short observational arc since its discovery leaves room for non-gravitational influences, forces caused by outgassing, that can subtly shift its trajectory over time, complicating precise long-term predictions. As new astrometric data continues to arrive from observatories around the world, the Minor Planet Center persistently refines its orbital models, aiming to determine whether Swan R2 is bound on a closed elliptical orbit, which would eventually bring it back into the inner solar system on a repeating cycle, or whether gravitational perturbations during this passage will propel it out of our reach, ejecting it permanently into interstellar space. The ultimate fate of Swan R2 remains uncertain, hinging on the ongoing accumulation and analysis of observational data as the comet journeys onward through the vast cosmic expanse. Current safety evaluations confirm that Swan R2 poses no imminent threat to Earth. Its closest approach will be at a distance of approximately 0.27 astronomical units, comfortably distant enough to ensure planetary safety, yet close enough to afford us a remarkable opportunity for detailed scientific examination of this intriguing visitor, originating from the far reaches of the outer solar system. Vigilant monitoring continues, with scientists and astronomers tracking the comet's precise trajectory to detect any unforeseen deviations that might influence these projections. The rapid evolution and breathtaking display of Swan R2 have captured the public's imagination, transforming it into a favored subject for outreach and educational initiatives worldwide. Astronomy clubs, planetariums, and educational institutions are actively weaving its appearance into their programming, leveraging its visibility as a compelling platform to illuminate topics such as comet formation, the architecture of our solar system, and the dynamic processes that sculpt the cosmic environment in which we reside. At the same time, professional observatories are beginning to incorporate Swan R2 into their observation plans, targeting it with spectroscopic and photometric instruments designed to analyze its composition and behavior. Although the majority of telescope time continues to be dedicated to the interstellar object known as 3I Atlas, due to its extraordinary origins and significance, Swan R2 offers invaluable insights into the makeup and activity of objects originating from the solar system's distant icy outskirts. The timing of Swan R2's appearance, coincidentally occurring in close temporal proximity to the passage of 3I Atlas through the inner solar system, presents an unprecedented comparative opportunity. These two distinct bodies, one an interstellar visitor and the other a native comet of our solar system's distant reservoir, are undergoing similar physical processes under comparable solar heating conditions. Such a scenario enables researchers to explore how their respective formation environments influence their physical and chemical behaviors, deepening our understanding of the diversity and complexity of cometary objects. This raises a profound question. If 3I Atlas acts as a scout, perhaps probing our cosmic neighborhood for information, then why does Swan R2 arrive like a grand herald, a cosmic city-sized sentinel, announcing something far more significant? The universe, with its penchant for surprises, rarely offers such a fortuitous juxtaposition for comparative study, making October of the year 2025 a month that could fundamentally reshape our understanding of the objects that traverse the vast expanses between and within stellar systems. Turning to the realm of speculative astronomy, where the boundary between the naturally occurring and the artificially engineered often becomes blurred, these observations ignite compelling theories about what might be possible in a universe teeming with intelligence yet to be recognized. The characteristics exhibited by 3I Atlas and Swan R2, while explainable through known natural processes, also invite provocative alternative interpretations, at least as mental experiments exploring the physics of directed propulsion, energy control, and deliberate design. A fundamental question concerns propulsion. Natural comets follow trajectories governed solely by gravitational mechanics, their paths shaped by the inverse square law and the initial conditions of their origin, be it formation in a protoplanetary disk or ejection from a distant stellar nursery. Any genuine propulsion system, however, would likely produce detectable deviations from these purely gravitational paths. Such deviations could include consistent acceleration vectors, attitude adjustments, or course corrections that fundamentally breach the principles of ballistic motion, revealing the presence of an active, engineered drive rather than a passive celestial body drifting through space. In essence, if these objects are truly propelled by artificial means, be it a plasma thruster, a reactionless drive, or some other advanced propulsion technology, such systems would manifest through observable anomalies in their trajectories. These might include subtle but persistent course corrections, unexplainable accelerations, or attitude shifts that cannot be accounted for by gravitational forces alone. Detecting such deviations would require highly precise measurements and continuous tracking, but their presence would serve as compelling evidence of engineered intervention, challenging the assumption of purely natural origins. A hypothetical plasma propulsion system operating by ejecting ionized gases at high velocities would leave unmistakable signatures in both the motion and electromagnetic emissions of its host object. The expelled plasma, forming an exhaust plume, would glow at characteristic wavelengths, the specific colors dictated by the composition and temperature of the ejected material. More critically, the thrust produced by such a drive would induce measurable shifts in the object's orbital parameters, with these deviations accumulating progressively over time into clear violations of Keplerian trajectories, those purely governed by gravity. However, what we observe in the case of 3I Atlas starkly contrasts with these expectations. Its trajectory, hyperbolic and consistent with an unbound object passing through our solar system, aligns with the natural path of a body influenced solely by gravitational forces. Its brightness and spectral changes follow predictable patterns that directly correlate with its decreasing distance from the Sun, known as heliocentric distance. The outgassing signals detected through our most sensitive instruments appear entirely consistent with natural sublimation processes, where solar heating causes volatile ices to vaporize and release gases, rather than artificial propulsion or engineering. Yet the timing of its arriving just miles from Earth within a narrowly defined window that coincides with Swan R2's closest approach to the Sun, raises eyebrows. This precise synchronization defies simple statistical likelihoods, hinting that the convergence might not be purely coincidental. If it is indeed coordinated rather than accidental, then it would imply the existence of propulsion systems so subtle and refined that they remain well hidden from our current observational capabilities. Such systems would operate at the edge of detectability, producing effects too faint or too cleverly masked to be distinguished with existing technology. Another layer of complexity involves electromagnetic shielding, a phenomenon where artificial objects might mimic natural plasma interactions. Comets naturally develop plasma sheaths, or ionized atmospheres, as the solar wind interacts with their expanding coma. These interactions naturally generate intricate magnetic field structures that deflect charged particles, shaping the characteristic anti-solar tail that streams away from the Sun. An active electromagnetic field system designed artificially could produce similar plasma behaviors, especially if it is intended merely to emulate natural phenomena. The subtle difference would lie in the configuration of the magnetic fields. Artificial systems might generate field topologies that serve purposes beyond simple solar wind deflection, such as facilitating communication, energy transfer, resource collection, or radiation shielding. Detecting these distinctions hinges on observing magnetic field structures that serve no natural function, patterns or topologies that imply intentional control rather than passive interaction. Currently, however, our observations of ion tails reveal behavior that aligns precisely with the expectations for natural comet-solar wind interactions. The James Webb Space Telescope, along with ground-based spectrographs, finds no anomalies, no unusual electromagnetic signatures, no coherent radio emissions, nor any evidence of controlled field generation beyond what natural physics would produce in an active comet. The orbital mechanics of these bodies, based on their scheduled paths, do not exhibit signs of systematic, purposeful maneuvering. Furthermore, long-period comets originating from our own Oort cloud can mimic the appearance of single, isolated objects, even when their orbits are mathematically closed ellipses, making the differentiation between natural and artificial trajectories extraordinarily challenging. These comets can follow complex paths that, due to gravitational influences, might appear random or unremarkable, yet in reality are consistent with natural gravitationally bound bodies. This confluence of factors, the absence of anomalous electromagnetic signatures, the natural behavior of plasma tails, and the orbital patterns, collectively suggests that despite the intriguing timing and spectral characteristics, these objects are consistent with natural phenomena rather than engineered spacecraft. Still, the possibility remains that some form of artificial manipulation might be operating at a level beyond our current detection threshold, cloaked behind the veil of natural appearance. Given that these celestial wanderers often have orbital periods surpassing even the span of recorded human history, any true pattern of systematic patrol or deliberate reconnaissance would eventually become evident through certain telltale signs. Such signs would include repeated appearances at regular, predictable intervals, almost like a cosmic clockwork, the coordinated arrival of multiple objects within tight time frames, or subtle trajectory modifications that seem to serve purposes beyond mere gravitational influence, hinting at strategic maneuvering or controlled propulsion. Since the 3 confirmed interstellar visitors identified since 2017, namely, the celestial object initially nicknamed Oumuamua, followed by the second known as Borisov, and now the third designated as Atlas, show no signs of such systematic spacing or orchestrated activity. The question of agency remains open but unconfirmed. These objects appear more like random natural visitors rather than evidence of an organized, intelligent patrol pattern. The astrophysicist Avi Loeb's response to the so-called signal hypothesis offers an intriguing thought experiment. What if our own electromagnetic emissions, our radio, television signals, and other transmissions, have unintentionally triggered automated responses from dormant monitoring systems scattered across our local galactic neighborhood? Such systems, if they exist, could be part of a vast distributed network designed to detect and respond to electromagnetic signatures from advanced civilizations. This scenario would naturally produce a correlation in timing. Perhaps the arrival of these anomalous objects coinciding with moments when our technological footprint in space has expanded, inadvertently alerting entities hidden or dormant within our stellar vicinity. It's a provocative idea suggesting that our own signals might be unwitting beacons, awakening or activating surveillance systems that have been lying dormant for eons. However, official space agencies like NASA and the European Space Agency remain steadfast in their position that the existing observational data align with natural explanations. Despite the strange properties exhibited by these objects, such as their unusual chemical signatures, their orbital mechanics, and their physical behaviors, both agencies emphasize the necessity of extraordinary evidence before jumping to extraordinary conclusions. The scientific community requires rigorous validation before considering non-natural origins. Analysis of the chemical signatures, the orbital trajectories, and the physical behaviors observed in both the interstellar object Atlas and the comet Swan R2 fall within the known spectrum of natural cometary phenomena. While these characteristics are at the exotic end, meaning they are unusual, they still conform to the physics of natural celestial bodies. For example, the observed nickel without accompanying iron signature in the spectrum of Atlas exemplifies how anomalous chemistry can be interpreted through two different lenses: natural or artificial. From a natural perspective, such a chemical fingerprint could be explained by processes like industrial or stellar nucleosynthesis pathways that concentrate certain elements or isotopes selectively. In particular, industrial processes, either on planetary surfaces or within the bodies themselves, might cause a selective enrichment of nickel, creating distinctive signatures in the exhaust or waste streams. Yet the detailed spectroscopic analysis conducted by the Very Large Telescope, VLT, includes discussions of several natural pathways. These encompass nickel-carbonyl chemistry, space weathering effects, and sublimation processes that could produce similar chemical fingerprints without necessitating any artificial origin. Color variations and behaviors like abrupt switching on or turning off, often observed in comets, further exemplify the ongoing debate between natural and artificial explanations. Comets typically exhibit nonlinear brightening curves as different volatile substances reach their sublimation points at varying distances from the Sun. This can give the illusion of discrete activation events, which some might interpret as propulsion systems coming online. Still, in reality, these are manifestations of the physics of ice sublimation in a vacuum environment, governed by well-understood thermodynamic principles. Distinguishing whether a comet's activity results from natural outgassing or artificial emission requires detailed analysis. Critical parameters include thrust vectors, acceleration profiles, and energy budgets, measurements that, if exceeding what natural sublimation could produce, might hint at engineered propulsion. At present, observational data show brightness and spectral variations that align precisely with the expected behavior of sublimating ice subjected to increasing solar flux. These signs are consistent with natural processes. The hypothetical presence of genuine technological engineering, such as onboard propulsion systems or controlled emission mechanisms, would likely be detectable through multiple observational channels. For instance, continuous thrusting or acceleration would over time produce measurable orbital perturbations, tiny deviations from a purely gravitational trajectory that could be identified with precise tracking. Detecting such deviations would require sustained, high-resolution monitoring over extended periods to establish a pattern beyond natural variability. In essence, current observations have yet to reveal any definitive signatures of artificial engineering. The orbital paths, spectral signatures, and brightness changes observed in both Atlas and Swan R2 all match the expected outcomes of natural ice sublimation processes driven by the physics of solar heating in space. Nevertheless, the potential for future detection remains. If artificial systems are operating, their effects would likely manifest as subtle, cumulative anomalies in the object's trajectories that might only be identified with even more precise long-term measurements. Thus, spacecraft and manufactured objects typically exhibit thermal signatures that set them apart from natural bodies, owing to their internal heat sources, specialized thermal regulation systems, or the presence of exotic materials. When scientists analyze the infrared emissions of interstellar visitors like 3I Atlas and Swan R2, their profiles consistently align with the expected glow of solar-heated ice and dust mixtures, much like cometary bodies formed in cold stellar nurseries. This congruence with natural thermal behavior strongly suggests these objects are not artificial constructs, but rather icy bodies warmed by the sun's radiation as they journey through our solar system. From a quantitative standpoint, the energy budgets implied by models of advanced technological systems, such as those necessary for interstellar propulsion, communication, or life support, are extraordinarily high. The immense energy expenditures required for such journeys, whether for accelerating to galactic speeds, maintaining onboard systems, or transmitting signals across vast interstellar distances, would likely leave detectable signatures. These might include anomalous electromagnetic emissions, unusual non-gravitational accelerations, or chemical compositions that defy natural formation processes. Yet, despite meticulous observations, no such indicators have been found in the data collected from 3I Atlas or Swan R2. The global astronomical community has established protocols, escalation procedures for responding to truly anomalous discoveries. If multiple independent observatories detected unmistakable signs of artificiality, such as structured repeatable signals, non-standard acceleration patterns, or impossible chemical signatures, coordinated efforts involving agencies like NASA, ESA, and others would swiftly mobilize to investigate further. These follow-up campaigns could include intensive spectral analysis, high-resolution imaging, and targeted radar measurements, all aimed at uncovering evidence of technological origin. However, to date, these procedures have not been triggered for either of these objects, indicating that their observed properties continue to fall within the scope of natural phenomena as understood by mainstream science. While the absence of artificial signatures strongly supports a natural explanation, it does not constitute definitive proof of natural origins. Our current detection capabilities, though highly sophisticated, may still be insufficient to identify subtle or highly advanced technological signatures, particularly if such systems operate beyond our present understanding or detection range. Consequently, the possibility remains open that some unknown or unrecognized form of technology might be present, but remains hidden from our instruments, underscoring the need for continued vigilance and technological advancement in our observational methods. In the realm of hypothetical advanced civilizations, it is conceivable that they harness propulsion methods, communication techniques, or material sciences so sophisticated that the signatures they produce remain beyond our current capacity to detect or understand. Our epistemological limitations, our fundamental inability to conclusively demonstrate the absence of artificial traits, leave ample room for ongoing speculation about the technological origins of these objects. This gap between what we are able to observe with our existing instruments and what might, in principle, be possible, opens the door to scenarios that defy definitive proof, given the constraints of our technological reach. This inherent uncertainty resonates deeply within the human psyche, as our innate desire to ascribe purpose and intelligence to phenomena that appear otherwise as mere coincidence compels us to seek explanations rooted in technology. The remarkable coincidence of the precise timing of both visitors' arrivals, their extraordinary characteristics, and their simultaneous convergence on our solar system during a period of rapid human technological progress forms compelling narrative patterns. These patterns, driven by our pattern-seeking nature, can be interpreted as potentially meaningful signals, an instinct to find intentional design amid the chaos of cosmic events. Analyzing the recent clustering of such objects through statistical means suggests that this apparent concentration might result from observational effects rather than an actual increase in visitation frequency. Over the past decade, our detection capabilities have improved exponentially, making us more likely to notice objects that, in earlier eras, would have passed unnoticed, hidden in the glare of the sun or too faint to detect. Since 2017, we have confirmed 3 interstellar visitors, designated as Oumuamua, Borisov, and Atlas, each initially confounding researchers with properties that challenged existing scientific frameworks but, upon more detailed analysis, aligned with natural explanations. This pattern of initial puzzlement followed by rationalization indicates that properties once thought extraordinary do not necessarily imply artificial origins. They can often be understood as natural phenomena even when they stretch the boundaries of our current understanding. Computer-based simulations of these objects' trajectories support the notion that our solar system naturally encounters interstellar visitors at a rate consistent with our observed sample. Assuming reasonable estimates of the density of such ejected objects in our local galactic environment. The timing and nature of these recent arrivals comfortably fit within the expected parameters for natural interstellar wanderers, suggesting that the phenomena we observe can be explained without invoking extraterrestrial technology. Nonetheless, the possibility persists that some fraction of these objects might be so technologically advanced that their features mimic natural processes perfectly, either intentionally designed or as an unavoidable outcome of engineering principles operating within the laws of physics as we understand them. Such objects, if they exist, would be virtually indistinguishable from natural bodies using our current observational methods. The ultimate assessment of whether these visitors are natural or artificial may hinge on their behavior during the most extreme phase of their journey, perihelion, when they pass closest to the sun. During this period of intense solar heating, both objects are expected to undergo their most significant thermal stress, potentially revealing features that remain concealed during their cooler approach. If they indeed harbor artificial systems, this stress could trigger responses, failures, or anomalies, such as sudden outgassing, structural shifts, or altered emissions, that might serve as indicators of their true nature. Observing these phenomena during perihelion could provide the critical evidence needed to differentiate between natural and engineered origins, offering insights into whether these objects are merely cosmic debris or something more deliberately constructed by an intelligence operating beyond our current understanding. Ground-based telescopes will soon face a critical limitation. As these objects draw nearer to the sun, the intense solar glare will render them invisible from our terrestrial vantage points. This creates a significant observational blind spot precisely during the most crucial phase of their journeys, when they are closest to the star and likely undergoing their most intense activity. The absence of direct, continuous monitoring during this period means that the definitive evidence supporting or challenging the idea of artificial origin might emerge just when we are unable to see it. In this context, observations from Mars orbiters, those spacecraft orbiting our neighboring planet, offer our most promising opportunity to maintain surveillance during this vital window. On October 3rd, 2025, During the flyby of the interstellar object designated 3I Atlas, these Martian instruments could provide crucial data to bridge the observational gap left by Earth-based telescopes. However, even the sophisticated sensors aboard these spacecraft face inherent limitations. Designed primarily for planetary science, mapping surface features, studying Martian atmospheres, and analyzing local geology, they are not optimized for detecting subtle signs of exotic phenomena or for identifying technological signatures in passing interstellar objects. Should these objects harbor genuine machinery, artificial constructs, or advanced probes, detecting them would demand observational capabilities and analytical techniques that push well beyond current astronomical practice. The subtlety of distinguishing a highly advanced, perhaps even deliberately engineered machine from a natural celestial body might be far more nuanced than our existing frameworks can reliably resolve. The challenge lies in recognizing artificial signatures that might be disguised within what appears to be a typical comet or asteroid. Signatures that, due to their sophistication, could resemble natural phenomena so convincingly that they evade detection unless we are specifically looking for them. This raises a profound question. Not whether we have already encountered evidence of alien technology, but whether, given the limitations of our instruments and understanding, we would even recognize it if it were hidden in plain sight. If an artificial machine were masquerading as a comet, what would it look like through our telescopes? Perhaps exactly what we currently observe, objects that challenge our scientific assumptions and stretch the boundaries of natural explanation, yet remain just plausible enough to avoid triggering the high thresholds of extraordinary evidence that scientific standards demand. The universe, with its vast complexity and depth, guards its secrets carefully, revealing them only to observers who are both sufficiently sophisticated in their questions and patient enough to accept that some answers may still be beyond our immediate grasp. Patience and inquisitiveness are essential virtues in this cosmic detective work, for the universe's most profound truths may require us to look beyond the obvious, to question our assumptions, and to remain open to possibilities that defy conventional understanding. Part 11. Shared Purpose. What might they have in common? In the grand theater of space, what initially appears as mere coincidence often begins to resemble deliberate choreography, once human minds start searching for patterns amid the chaos. When two visitors arrive within a span of weeks, displaying characteristics that complement each other and following paths that converge on our sun during a narrowly defined window, it begins to seem less like chance and more like a coordinated sequence. An orchestrated part of a larger design if we allow ourselves to fill in the gaps left by incomplete data. Imagine for a moment that Swan R2 functions as a mobile depot, an advanced resource station or relay node, while 3I Atlas acts as a nimble reconnaissance probe, gathering intelligence and relaying information. In this speculative scenario, the massive comet, with its sprawling tail and apparent volatility, is not merely a natural ice body. Instead, it could be a highly sophisticated logistics platform, designed with controlled resource management and integrated communication systems concealed beneath its seemingly chaotic exterior. Its volatile appearance might mask a carefully engineered system, orchestrating resource transfers, data exchanges, or even signals that we have yet to interpret. Such a framework invites us to consider that these objects are not passive wanderers, but active participants in a larger, perhaps deliberate operation, an elaborate network of technological infrastructure woven into the fabric of space. The apparent randomness of their activity and trajectories might be illusions, masking a complex web of controlled resource flows and communication channels, all orchestrated with a purpose that remains hidden from our current understanding. The diminutive yet highly agile object, designated as 3I Atlas, likely functions as an advanced reconnaissance vessel. an intelligence-gathering scout assigned to observe and analyze the characteristics of our solar system. Its primary role would be to relay crucial information back to a larger, more substantial installation, which could serve as a hub or processing station. This configuration, where a smaller scout coordinates with a larger depot, helps make sense of several perplexing aspects of their observed behavior. For instance, the precise timing of 3I Atlas's approach, along with its carefully calculated trajectory, suggests deliberate navigation towards specific prearranged coordinates, destinations where Swan R2 might be stationed to receive data, transfer vital resources, or carry out maintenance and repairs. What we interpret as unusual outgassing signatures could, in this context, actually be controlled emissions. Deliberate releases of fuel, atmospheric processing byproduct, or other operational byproducts of sophisticated technological systems functioning under extreme thermal conditions. This perspective posits that the observable chemical signatures are not solely natural phenomena, but may be signatures of engineered activity, possibly involving precise regulation of gas release and energy management. An alternative hypothesis suggests that both objects are not necessarily artificial constructions, but rather natural bodies, asteroids or comets, that have been opportunistically repurposed by an ancient, widespread monitoring network scattered across our galactic neighborhood. Instead of purpose-built spacecraft, they might be commandeered celestial objects whose surfaces or interiors have been modified to serve as platforms for autonomous, perhaps even self-activating systems. These systems could be designed to spring into action when specific conditions are detected, such as the electromagnetic signals indicating the emergence of technological civilizations. This piggybacking approach could explain why both visitors exhibit characteristics that hover at the edge of what appears natural. Their behaviors and signatures are subtly anomalous but still within the realm of plausible natural phenomena. Any civilization capable of establishing such an interstellar monitoring network would likely prioritize stealth over overt detection. To avoid provoking defensive responses from encountered species, such beings might employ camouflage and mimicry, disguising their activity within the natural environment of space. Transforming natural objects, asteroids and comets, into covert functioning platforms offers an ideal cover, allowing artificial systems to blend seamlessly among the countless rocks and icy bodies drifting through interstellar space. Furthermore, the sun itself might serve as more than just a gravitational anchor or a source of illumination. It could be an integral component of this cosmic infrastructure. Solar radiation provides a seemingly inexhaustible energy source, perfect for systems designed to harvest electromagnetic energy. Simultaneously, the solar wind, streams of charged particles emanating from the star, creates a dynamic plasma environment, which might support exotic physics principles far beyond our current understanding. These ionized winds flowing away from the star could act as both a means of communication and a power source for advanced technologies, operating on principles yet to be fully comprehended. Envisioned as part of a sprawling surveillance grid, these hypothetical networks of nodes might be strategically positioned at optimal locations within stellar systems to monitor planetary development and the rise of technological civilizations. The sun's deep gravitational well could serve as a natural hub, collecting, aggregating, and relaying information from distant sensors, then processing and transmitting data to even more remote stations. The apparent convergence of these objects in October 2025 might be no coincidence but a routine operation, a data collection and relay maneuver designed to gather intelligence across the galaxy. Yet this same timing could also point to a more ominous interpretation, the hunter and harvested dynamic, where the convergence signals a predatory or resource extraction operation. In this scenario, the coordinated approach of these objects might be part of a calculated, potentially aggressive strategy, one that involves monitoring, gathering, and perhaps even exploiting or controlling resources within our solar system. The implications of such a duality, either benign observation or strategic harvesting, add a layer of complexity to the ongoing debate about their true nature and purpose. If we entertain the notion that 3I Atlas functions as a predatory system, an advanced observer tasked with identifying and neutralizing potential threats, then Swan R2 might serve as a dedicated resource processing platform, designed to handle whatever materials or information the hunter gathers. The stark contrast in scale between the agile scout and the colossal processing installation reflects their specialized roles within a broader operational framework. This perspective suggests that our solar system is viewed not merely as a passive neighborhood, but as a domain of opportunity or danger, depending on the observer's intent. Imagery arising from this speculative scenario paints a vivid picture. The small courier spirals inward, approaching a designated rendezvous point while the greater installation unfurls complex arrays of collectors and processing systems preparing to convert, analyze, or utilize the materials or data delivered. What appears as cometary activity, the shimmering tail, the brightening nucleus, might actually conceal far more deliberate and purposeful operations. These could include energy harvesting, matter transformation, or even the assembly of temporary infrastructure meant to support prolonged activity in our vicinity. It's crucial to acknowledge that such scenarios reside firmly within the realm of imagination, unsupported by direct observational evidence. Yet they are compelling enough to seize human attention precisely because they lend a narrative structure to phenomena that otherwise seem random or devoid of meaning. The human mind instinctively resists the idea of mere coincidence. Instead, it seeks explanations rooted in intention and design. This tendency to interpret patterns as purposeful reflects deeper philosophical questions. What constitutes intelligence in the universe, and how can we recognize it, especially when it manifests in forms utterly unfamiliar to us? If advanced civilizations routinely operate with technologies capable of mimicking natural phenomena, deceiving us into believing we observe purely natural events, how can we distinguish between genuine cosmic processes and sophisticated artificial systems? The clustering of such events in October, forming a chronological sequence of perihelion passages and close approaches, provides a real temporal framework upon which these speculative stories can be constructed. The sequence: Swan R2's approach on September the 12th, 3I Atlas's flyby near Mars on October the 3rd, the subsequent perihelion of 3I Atlas on October the 29th, and Swan R2's closest approach to Earth on October the 21st, could either be an extraordinary coincidence or a carefully choreographed sequence, planned by an intelligent design. Throughout human history, mythic parallels serve as templates for interpreting the unknown. Cultures worldwide have legends of celestial visitors heralding major epochs, lights in the sky that foreshadow the rise of empires, the fall of civilizations, or the dawn of new knowledge. Could 3I Atlas and Swan R2 be modern echoes of these archetypal stories? Might they represent a form of cosmic messaging, a deliberate pattern echoing our ancient myths? The recurring question that echoes throughout this line of speculation remains: is this simply a comet, a fortress, or the reply to a message we never knew we sent? When applied to paired visitors rather than isolated anomalies, this inquiry gains profound new layers of meaning. Are they mere natural objects coincidentally arriving together? Or are they part of a larger orchestrated choreography? Perhaps a communication or reconnaissance protocol from a civilization far beyond our understanding? The pattern, the timing, the scale, all seem to hint at something beyond chance, inviting us to ponder whether these celestial events are signs, symbols, or signals crafted by intelligence seeking to engage with us in a language of cosmic design. If one of these objects embodies the message and the other the reply, their simultaneous arrival and convergence could signify the culmination of a long-standing dialogue, an exchange that perhaps began many decades ago when our own radio signals first pierced the vacuum of space, leaking outward into the cosmic abyss. This possibility ignites a profound sense of connection, suggesting that what we send into the void might eventually receive a response, encoded in ways beyond our current understanding. Yet, as with any narrative of cosmic communication, caution is paramount, and guidance becomes essential at this juncture of exploration. For we have now crossed from the realm of concrete data into the perilous territories of pure speculation, abandoning the firm grounding of observations for the shimmering yet treacherous waters of imagination and theoretical possibility, the factual anchors that have supported our investigation, the precise timing of the October encounters, the spectral signatures indicating complex chemical compositions, the orbital mechanics that align with natural celestial phenomena, continue to uphold natural explanations. Still, they also serve as fertile ground for more exotic interpretations, ideas that challenge our conventional understanding. The notion of a shared mission implying coordination between these objects remains an assumption rather than a confirmed fact. Such an orchestrated purpose has yet to be proven. The simplest explanation, perhaps, is that these events are the result of purposefully aligned incidents, an occurrence rooted in natural processes where apparent signs of intelligence are mere illusions or incidental coincidences. In our human quest for meaning, the drive to find patterns and purpose in these phenomena is as strong as our desire for scientific clarity. These psychological needs naturally influence how we interpret ambiguous signals from the cosmos. Nonetheless, we cannot dismiss the possibility that some forms of advanced technology, possibly crafted by civilizations far more sophisticated than ours, might operate so seamlessly that their actions mimic natural processes perfectly. Such technology could be intentionally designed or an inevitable product of engineering principles that work in harmony with the unyielding laws of physics rather than against them. Detecting such subtle signs would demand methods and analytical frameworks that surpass our current scientific capabilities, tools that can discern artificial intent hidden within what appears to be natural behavior. The ultimate test of these shared purpose theories may unfold during the upcoming solar encounters. When these visitors plunge into the sun's intense heat, they may reveal traits and anomalies concealed during their approach, manifestations of technology or coordination that remain hidden in the cooler, less active phases. Perihelion, the closest point to the sun, becomes a critical moment when energy demands and communication needs might reach their zenith, potentially exposing signs of deliberate synchronization. However, during this same period, the sun's overwhelming glare creates an observational blackout, a gap that prevents us from directly witnessing what transpires during these crucial moments. This celestial curtain could obscure definitive evidence, leaving us to speculate whether these objects act in concert or operate independently. In the aftermath of the October silence, we might emerge with refined data, confirming they are merely natural celestial phenomena. Or we might face findings that challenge our deepest assumptions about what passes through the darkness between stars. If they indeed share a mission, what purpose would require both a scalpel, a precise, perhaps surgical tool, and a factory, a place of production or processing? The answer might be inscribed in the fiery heart of our sun during those covert weeks when these cosmic travelers perform their final dance within our view, before slipping away into the depths of cosmic memory and myth. This brings us to the intriguing relay hypothesis, a concept rooted in the realm of speculative astronomy, where imagination intersects with the fundamental laws of physics. It is a scenario that captures a sense of cosmic purpose, suggesting that these objects might serve as components of a vast, deliberate information network. The idea posits that the interstellar object known as 3I Atlas functions as a data courier, carrying compressed archives of observations from its journey through the galaxy. While Swan R2 acts as a processing hub and transmission node, working in concert to exchange information through the glowing canvas of our star. Their convergence on the Sun, therefore, may be part of a long-planned, meticulously coordinated operation, an intricate dance of data, energy, and purpose that has been unfolding over years or even decades in preparation. Envision a celestial messenger, an object designated as 3I Atlas, descending from the depths of interstellar space, bearing within it a compressed archive of observations amassed over a journey spanning countless light-years through our local galactic neighborhood. Despite its modest dimensions and agile trajectory, this craft suggests an optimization for swift maneuvering and rapid data transfer, rather than the sheer capacity of bulk storage. Yet even a seemingly small object can harbor vast repositories of information if encoded with advanced, perhaps even undiscovered storage technologies capable of packing immense data into minimal volume. The peculiar chemical signatures detected in its spectral analysis might not be mere byproducts of natural outgassing. Instead, they could represent carefully controlled data, information inscribed into physical substrates, deliberately transmitted and inscribed as the courier approaches its scheduled rendezvous point in our solar system. Meanwhile, another object, Swan R2, emerging from the distant icy outskirts of our own solar system, presents a contrasting profile. Its sprawling tail and immense apparent scale evoke the image of a colossal data processing hub, a sophisticated processing and relay station designed for interstellar communication. Its dramatic tail development, rather than being solely a natural cometary feature, could conceal intricate arrays of collection instruments and transmission systems, engineered to operate under the extreme conditions encountered near a star. What appears to be cometary activity, brightening, tail formation, might mask precisely directed energy beams, plasma manipulation systems, or other exotic communication technologies. These could function by modulating interactions with the solar wind, effectively bending and harnessing the plasma environment as a medium for transmitting information across vast cosmic distances. The star at the heart of this hypothetical network, the Sun, becomes an integral, perhaps even vital, third component of this interstellar relay system. Our star is not merely a source of light and warmth. It embodies the universe's most potent energy reservoir within hundreds of astronomical units, capable of powering systems far beyond the reach of portable energy supplies. But the Sun's significance extends well beyond its raw power. It creates a uniquely conducive environment for advanced physics applications. Its gravitational field can act as a natural lens, an idea rooted in Einstein's general relativity, focusing electromagnetic signals across staggering distances, effectively transforming the star into a cosmic amplifier or a natural telescope. Such gravitational lensing could facilitate interstellar communication by concentrating signals at specific points known as gravitational focus regions, strategically placed throughout the galaxy, where stars themselves serve as relay stations in a vast, star-powered communication network. Furthermore, the plasma environment surrounding the Sun introduces additional avenues for exotic physics to be harnessed. The solar wind, a continuous stream of charged particles, permeates the solar system, establishing vast currents and complex magnetic field structures. Highly advanced civilizations might manipulate these natural phenomena, writing information directly into plasma flows, encoding messages in the configurations of magnetic fields that stream past planets and into the interstellar medium. Imagine systems that don't rely solely on conventional electromagnetic signals but instead utilize the plasma itself as a medium, modulating its properties, creating dynamic patterns that serve as long-distance communication channels. Such a process would be analogous to a cosmic-scale data transfer, with the solar environment acting as a colossal natural data highway. In this scenario, Swan R2's apparent activity, its dust and gas clouds, its bright tail, becomes a sophisticated guise. The collection surfaces it unfurls, and the radiation it harvests could be masking highly engineered functions, such as directed energy beams, plasma manipulation arrays, or other exotic communication infrastructures, integrated seamlessly into what appears as natural cometary phenomena. This colossal system, operating at a scale that makes photosynthesis seem primitive by comparison, could be capturing solar radiation with unmatched efficiency, converting the star's energy into signals and data streams designed for interstellar relay, an invisible industrial-scale operation concealed behind the guise of a celestial visitor. Advanced systems for storing information have evolved to the extent that they inscribe data into crystalline matrices, materials capable of withstanding the relentless assault of interstellar radiation, extreme temperature fluctuations, and cosmic dust. Within these formidable structures, a digital fortress is built, an edifice bathed in ionized plasma where terabytes, vast quantities of compressed intelligence flow seamlessly between interconnected systems. These operations occur at the very intersection of matter and energy, a zone where physical and informational realms merge into a cohesive, resilient network. The idea of harnessing stellar radiation, drawing power directly from the sun's immense energy output to fuel data operations reflects the staggering power demands such an interstellar communication system would entail. Transmitting signals across galactic expanses necessitates energy expenditures so vast that they push the limits of what even stellar-scale resources can sustain. This challenge is not merely technological but fundamental. To send meaningful messages over hundreds or thousands of light years, civilizations would need to develop energy harvesting and transmission methods far beyond our current scope. In this context, the October of 2025 might stand out as a uniquely favorable convergence point. During this period, the dynamic interplay of solar activity, planetary alignments, and the positioning of receiving stations could create an optimal window, an ideal alignment, allowing for the most efficient and powerful data transmissions possible. It's a fleeting window in cosmic time, but one where the conditions align perfectly. Solar flares, magnetic field orientations, and planetary positions coalesce to maximize the potential for successful interstellar messaging. Our planet's own electromagnetic emissions, the radio bubble we have generated since the dawn of the modern age, serve as the trigger for this speculative operation. Since the 1920s, human civilization has been leaking electromagnetic signals into space, radio, television, radar, and now digital communications, forming an ever-expanding sphere of artificial signals that currently stretches approximately 100 light-years in all directions. To any monitoring system stationed within this bubble, artificial or natural, these signals are unmistakable evidence of an emerging technological civilization, a kind of cosmic handshake announcing our presence. This electromagnetic footprint could, in theory, have triggered the activation of dormant relay networks, preconceived, long-established infrastructure meant for this very purpose. These networks, scattered across the galaxy, might be waiting silently, ready to respond when certain thresholds of technological development are reached, or specific signals are detected. The precise timing of our own technological progression, coupled with the recent appearance of unusual interstellar visitors, lends new weight to this hypothesis. If intelligent monitoring systems had been tracking our radio leaks for decades, they would have needed time, possibly centuries, to dispatch interstellar couriers, navigate the vast void, and coordinate operations with local relay stations positioned at strategic points across the galaxy. The current wave of visitor objects, strange, unexplained bodies from beyond our solar system, could plausibly represent the response phase of this interstellar communication protocol, an active reply to signals we inadvertently sent into the depths of space long ago. Yet the universe's reality remains unaltered by our speculative scenarios. Despite these imaginative possibilities, no concrete evidence of such an exchange has been observed. No narrowband radio signals, signatures that would be the unmistakable hallmark of intelligent communication, have been detected from either visitor. Similarly, no controlled propulsion or attitude adjustments, which might suggest deliberate maneuvering by an artificial craft, have been measured. Their chemical signatures and physical behaviors continue to fall within the realm of natural cometary phenomena, though at the more exotic, less common end of the natural spectrum. NASA's official stance reinforces this perspective. The agency emphasizes that current observations are consistent with natural explanations, not evidence of alien technology. Their scientists remind us that extraordinary claims require extraordinary evidence. And despite the unusual characteristics of these objects, neither the chemical signatures nor the physical behaviors observed so far surpass what natural processes can produce under certain conditions. This cautious position underlines a fundamental principle of scientific inquiry: the importance of evidence-based conclusions, especially when dealing with phenomena that can be explained by well-understood natural physics. The question of who sent them, the speculative inquiry that has captivated many, leads us down numerous pathways of thought. Some consider the possibility that these objects are messages from our own future, sent back in time or through some form of advanced interstellar communication that transcends our current understanding of physics. Others ponder whether they are remnants of an ancient, long-dead civilization's infrastructure, cosmic fossils, so to speak, left behind as a kind of galactic relay station or monitoring network, quietly observing and perhaps even influencing emerging civilizations like ours. In the end, these reflections reveal more about human psychology, the innate desire to find meaning, purpose, and intentionality in the cosmos, than about extraterrestrial visitors themselves. Our minds are wired to seek patterns and narratives, to interpret anomalies as signs of deliberate intent. Whether they are messages from the future, artifacts of ancient galactic civilizations, or purely natural phenomena, the true nature of these objects remains shrouded in mystery, inviting both cautious. Some have proposed that these objects might be sent back through a manipulation of space-time itself, enabling information to travel backward not only across vast distances but also through the fabric of time. Such a concept suggests that these entities could originate from parallel evolutionary lineages, advanced civilizations that achieved interstellar capabilities millions of years ago, and have since been secretly monitoring the development of intelligence within our local galactic neighborhood. Alternatively, these objects could be mere fragments of an ancient, automated network, remnants of a once thriving civilization that mastered interstellar travel long before Earth even formed. Over eons, this civilization might have vanished, leaving behind only an intricate infrastructure of monitoring and communication devices that continue to operate autonomously, executing their original programming regardless of their creator's absence. In this scenario, we are not necessarily dealing with active, conscious intelligence, but rather with the enduring echoes of a long-extinct technological civilization, fossilized remnants that persist as silent witnesses to a bygone era. These systems, programmed to function over unimaginable timescales, keep executing their directives, maintaining surveillance or relaying data without any current consciousness behind them. However, a critical examination of the practicality of an interstellar relay network reveals formidable challenges rooted in energy requirements and the laws of physics. To broadcast coherent signals across interstellar distances, a civilization would need to allocate power levels that constitute a significant fraction of its star's total output. The sheer energy expenditure necessary to maintain such communication would be staggering, placing it beyond the reach of most conceivable civilizations based on our current understanding. Equally daunting are the technical demands on receiving infrastructure. To detect and interpret such signals, enormous antenna arrays, comparable in size to planets, would be necessary, demanding levels of technological and industrial capacity that surpass anything humanity has achieved or even imagined. Yet these limitations are based on the assumptions of physics and engineering principles familiar to us, principles rooted in our current technological framework. Civilizations that have advanced beyond our limitations might employ technologies operating on principles that render our concepts of energy and communication obsolete, much like how early humans relied on smoke signals before the advent of fiber optics. What appears impossible to us today could become routine for a species that understands and harnesses physics at a level far more sophisticated than ours. Just as our present capabilities would seem miraculous to past generations. Think of how unimaginable space travel or digital communication would have seemed a few centuries ago. So too might their technologies be beyond our understanding. The relay hypothesis offers a compelling narrative, transforming the seemingly random encounters with cosmic objects into purposeful acts of intelligence. Signals sent or received as part of an ongoing, deliberate exchange. It implies that humanity has reached some threshold of technological evolution that makes us observable and potentially even interesting to more advanced civilizations. Those that monitor galaxy-wide development for signs of emerging intelligent life. If true, it suggests that we are not entirely alone nor entirely overlooked, that forces operating on incomprehensibly vast scales are observing, guiding, or at least paying attention to our progress. Nevertheless, this hypothesis demands that we accept claims of purpose and coordination based on evidence that, in many ways, remains remarkably ordinary. The observed phenomena, unusual chemical signatures, peculiar orbital behaviors, are consistent with natural processes. Yet they are interpreted through a lens that ascribes an extraordinary purpose to them. The idea that these objects are part of a deliberate relay system hinges on the assumption of coordination where none has definitively been demonstrated, and on purpose where simpler explanations, chance, natural formation, or incidental alignment, could suffice. The upcoming convergence in October of 2025 will serve as a crucial testing ground for such relay hypotheses. It offers the opportunity to observe whether these objects demonstrate signs of intentional communication, coordinated movement, or other behaviors characteristic of an active, purposeful system, if such signs exist at all. Until then, the question remains open. Are we witnessing the distant echoes of an ancient intelligent network, or merely the natural wanderings of cosmic debris shaped by physics we understand? If genuine data transmission truly takes place between our visiting objects, it would most likely become evident during their closest encounters with the Sun, when the energy available reaches its zenith, and the optimal windows for communication align. The central challenge lies in differentiating these potential signals from natural cometary phenomena, those familiar outbursts of dust and gas, especially since any artificial information processing systems operating in such extreme thermal and radiation environments would leave signatures that are subtle, complex, and difficult to distinguish from natural processes. Consider the possibility that the handoff, an exchange of information, could occur precisely during the period when our telescopic eyes are rendered blind, concealed behind the overwhelming glare of our star during the most critical phase of their passage. In such a scenario, when the moment of maximum activity coincides with the greatest observational obscuration, We might emerge from the October silence having gleaned nothing more than refined measurements of ice sublimation rates and dust dynamics, data consistent with natural comet activity. Alternatively, it's conceivable that we could confront unmistakable evidence suggesting that our solar system is not just a passive recipient of celestial visitors, but a vital node in a galaxy-spanning communication network. This relay hypothesis elevates our sun from its familiar role as a solitary star to that of a cosmic post office, an active hub where messages are exchanged, routes are routed, and information is transferred across vast interstellar distances. In this framework, our visitors, once seen merely as wandering objects, are reinterpreted as mail carriers, messengers, completing routes that originated in distant stellar systems whose names we may never know. Whether this transformation reflects a genuine discovery or simply the human tendency to impose meaning upon chaos remains the core mystery of our current cosmic moment. Now, turning to what we call the harvest scenario, a vision of cosmic resource extraction raises profound questions about the true nature of our star. The sun has burned for roughly 4.5 billion years, a relentless forge of nuclear fusion converting vast quantities of matter into energy, about 4 million tons each second, powering the very fabric of our existence. Yet what if this celestial furnace functions not solely as the engine of our solar system's life, but also as a cosmic fuel station, a source of exotic energies and materials that advanced civilizations might harvest on timescales measured in thousands or even millions of years, rather than human generations? Imagine 3i Atlas and Swan R2 as components of an automated harvesting operation, arriving at our star not by random chance but following a pattern established long before humans ever roamed the African savanna. The smaller object acts as a surveyor and coordinator, measuring stellar output, plasma conditions, and magnetic activity, aimed at optimizing the efficiency of resource collection. Meanwhile, the larger installation deploys collection systems that are cleverly disguised as natural cometary activity, siphoning energy and materials from the sun's outer atmosphere. These systems would operate at the crossroads of engineering and physics, utilizing technologies that are far beyond our current understanding. This scenario compels us to reconsider the spectacular cometary displays we observe, those luminous tails and sudden outbursts, as nothing more than camouflage for industrial processes. Swan R2's magnificent tail, stretching across degrees of the sky, might actually conceal engineered magnetic funnels designed to channel solar wind particles into hidden processing systems. These systems could be hidden within what appears to be a natural coma, their true purpose masked by the appearance of a typical celestial visitor. The ion tails we interpret as passive responses to charged particle pressure. The anti-solar directions might instead be controlled exhaust plumes, carefully directed by sun farming engines operating on scale and sophistication that make our most advanced industrial enterprises look primitive. In this light, the celestial displays we see are not simply natural phenomena, but a form of industrial camouflage, an elaborate cover story for the harvesting of stellar energy. These systems could be harnessing the sun's vast power, manipulating magnetic fields and plasma flows to extract fuels, rare elements, or even exotic particles, resources vital for civilizations that command technology at a galactic scale. The idea challenges our understanding of natural processes, suggesting that what we see as cometary tails might be, in fact, the visible signatures of controlled engineering, evidence of a cosmic infrastructure dedicated to harvesting and perhaps even managing the star's energy for purposes we can only begin to imagine. These hypothetical magnetic collection systems would need to operate with an extraordinary level of subtlety and precision to evade detection by our increasingly sophisticated observational instruments. Unlike the crude, obvious machinery we might imagine, Advanced civilizations might have long since mastered the art of working harmoniously with natural forces rather than opposing them. Instead of deploying overtly artificial devices, they could engineer technologies that seamlessly enhance and direct the inherent processes of the universe, subtly steering natural phenomena toward their resource extraction goals. What we perceive as ordinary cometary activity might in fact be a highly optimized expression of natural ion acceleration mechanisms, carefully calibrated to serve the needs of resource harvesting. The physics underlying such operations would stretch the boundaries of our current understanding, reaching into domains where the laws of physics become increasingly complex and less familiar. One intriguing possibility is that these civilizations utilize micro-wormhole networks, tiny transient portals stabilized by the extreme gravitational and magnetic field conditions that naturally occur near stellar surfaces. These microscopic space-time conduits could facilitate instantaneous or near-instantaneous transport of harvested materials across vast interstellar distances. Such a system would effectively eliminate the need for conventional propulsion, allowing resources collected in one star system to be transferred rapidly to distant hubs or civilizations. The extreme fields necessary to sustain these wormhole networks would be rare and naturally occurring, existing predominantly in environments like stellar coronas, regions where magnetic field strengths can reach thousands of times greater than those at Earth's surface. In these zones, the intense magnetic and gravitational conditions approach the limits where general relativity's effects become significant, providing the perfect environment for the formation and stabilization of these conduits. Our Sun, during its active phases, might be strategically exploited by these visitors, positioning themselves to harness these unique physical conditions during brief windows when the magnetic field geometries align favorably for exotic physics applications. The cycles of solar activity, such as the approximately 27-day rotation period, generate natural rhythms in magnetic field orientation and plasma density. These rhythms could be precisely exploited by highly advanced harvesting systems, which might synchronize their operations with these cycles to maximize efficiency, akin to a cosmic dance with the star's natural cadence. October of the year 2025 could represent an ideal window for such resource extraction, dictated by long-term solar cycles and magnetic field configurations aligning in just the right way. Additionally, the composition of the solar wind itself offers another potential target for these operations. The Sun naturally produces helium-3 through its fusion processes, a lightweight isotope that is considered an excellent fuel candidate for advanced nuclear reactors by human researchers. Although the concentrations of helium-3 dispersed throughout the solar system are far too sparse for current human exploitation, a civilization with vastly more advanced separation and concentration techniques could, during close stellar approaches, gather useful quantities from the solar wind. Resource extraction in this context would extend beyond merely harvesting fuel. It could involve tapping into exotic forms of matter and energy that are only stable or accessible within stellar environments. The extreme temperatures and pressures in the stellar chromosphere could facilitate the creation of exotic matter states, such as quark-gluon plasmas, magnetic monopoles, or other theoretical particles predicted by high-energy physics. These substances could serve as potent energy sources or as advanced materials for manufacturing, enabling civilizations operating on galactic scales to harness the universe's most fundamental and energetic phenomena. In essence, these processes might be akin to cosmic alchemy, transforming stellar material into resources vital for their sophisticated technological infrastructure, all while remaining hidden from our current observational reach. Historical patterns of human resource extraction offer valuable frameworks for imagining how stellar harvesting might unfold on a cosmic scale. Throughout our own history, early humans relied heavily on seasonal migrations to exploit fleeting concentrations of game animals edible plants and raw materials, strategic movements driven by the availability of resources in particular regions. As civilization advanced, these practices evolved into permanent infrastructural settlements, often established near vital sources like coal deposits, oil fields, and mineral-rich regions, shaping where cities grew and transportation networks developed. This progression from temporary exploitation to permanent resource hubs illustrates a natural drive to maximize resource efficiency, a pattern that now extends, at a vastly larger scale, into the realm of stars and cosmic energy. Transposing this familiar pattern onto the universe, stellar harvesting can be seen as the logical and inevitable extension of resource exploitation into the stars. Civilizations capable of interstellar travel may develop technologies to tap into the immense energy and materials stored within stars themselves, much as humans have historically extracted from Earth's deposits. But such operations would have profound implications beyond raw resource collection. They demand an understanding of and adaptation to the physical environment of stellar systems, particularly the electromagnetic phenomena that underpin space physics. The implications for sound design, though space itself is a vacuum, are equally compelling. In the emptiness of space, no acoustic waves can travel, and there's no medium for sound as we understand it. Nevertheless, if advanced civilizations are engaging in stellar resource extraction, their activities might produce electromagnetic signatures that are, in effect, the spacefaring equivalent of sound. These signals, transmitted via radio frequencies or magnetic field interactions, could form distinctive patterns that, if decoded, would reveal the presence of such operations. For example, slow rhythmic pulses in radio frequencies, akin to the thumps of a mechanical heartbeat, might be generated by machinery maintaining station within a star's intense gravitational and magnetic environment. Similarly, distant crackles or fluctuations could result from magnetic field lines reconnecting and releasing energy. Phenomena well understood in plasma physics but potentially used for purposeful communication or control. Any genuine stellar harvesting operation would require constant station keeping, continuous adjustments to a craft's attitude, position, and stability to counteract the complex and dynamic forces exerted by the star's gravity and magnetic fields. These ongoing maneuvers would leave measurable signatures in the trajectory and rotation states of the objects involved. Our instruments, with increasing sensitivity, should in principle be capable of detecting such signatures if they exist. The absence of detectable anomalous movements or rotational anomalies in our current observations, therefore, argues against the idea that these objects are actively engaged in resource extraction. However, we must remain cautious in our assessment. Our detection capabilities are inherently limited, and it is conceivable that highly advanced systems operating thousands of years beyond our technological understanding could manipulate magnetic fields or electromagnetic signals in ways that are undetectable with current instruments. These hypothetical systems might maintain position and orientation with such subtlety that their signatures fall below the thresholds of our measurement systems, effectively cloaking their activities. What we interpret as natural cometary behavior, such as tail formation and brightness variations, might in fact be the precise result of complex industrial protocols executed with extraordinary precision, subtly mimicking natural processes to avoid detection. This leads us into profound ethical questions about the nature of property rights and territorial claims on a cosmic scale. If advanced civilizations routinely harvest energy and materials from stars throughout the galaxy, does our own sun belong to everyone, or does our presence in its orbit establish some form of territorial claim? Would such civilizations view emerging life forms, like humanity, as mere biological phenomena, irrelevant to their resource management, or as potential competitors? Moreover, could the signatures of natural comet behavior be distinguished reliably from those of engineered harvesting? For instance, ion tails, formed by charged particles pushed away from the sun by radiation pressure, are well understood phenomena governed by known physical laws. Any industrial operation designed to harvest stellar energy would need to conform to these physical constraints or risk producing detectable anomalies, violations of the expected tail geometry or plasma behavior. That would reveal its artificial nature. In essence, the universe's natural laws set boundary conditions that any genuine stellar harvesting operation would have to obey or risk detection. The tail of a comet, shaped by radiation pressure and charged particle interactions, points away from the star in predictable ways. To remain undetected, artificial systems would need to operate within these constraints, perhaps subtly manipulating plasma flows or magnetic fields to mimic natural phenomena. Currently, our observations through spectroscopic analysis and plasma physics models show no signs of such violations. The ion tails we observe follow the expected patterns, and the electromagnetic signatures align with natural processes, suggesting that, if stellar resource extraction is occurring, it remains meticulously concealed. In summary, while the parallels with human resource extraction provide a compelling lens for understanding potential stellar harvesting, the physical signatures, tail geometry, electromagnetic emissions, plasma interactions, serve as the cosmic fingerprints we can detect and analyze. To date, the evidence aligns with natural cometary behavior, but the universe's vastness and the limit. Our current observations reveal that the behavior of the ion tail aligns precisely with well-established theoretical models for natural comets interacting with solar wind. There is no evidence of unexpected accelerations, no deviations in tail orientation that would suggest external manipulation, and no signs of controlled magnetic field generation beyond what innate plasma physics would produce. Spectroscopic data further confirm this natural origin, displaying molecular signatures consistent with familiar chemical processes driven by solar heating. If by some chance stellar harvesting operations were actively at work within our solar system, we would anticipate detecting atypical non-gravitational influences or orbital anomalies, distortions that indicate systems maintaining optimal positions relative to the sun's variable conditions. Yet our meticulous tracking of both objects, 3I Atlas and Swan R2, shows no such signatures, implying that their movements are governed solely by gravitational forces, not by artificial mechanisms. Nevertheless, the idea of cosmic harvesting retains a certain psychological allure, because it recasts these seemingly random celestial encounters as components of a vast, sophisticated industrial enterprise spanning the depths of space and the eons of time. It suggests that our sun might serve purposes beyond merely supplying energy for life on Earth. Perhaps it is part of an intricate network of resources and information exchanges operating on scales that defy human comprehension. The convergence in October of two such visitors, one from interstellar space and the other from our own distant cloud, becomes more than a mere orbital coincidence. It transforms into a moment of cosmic commerce, a fleeting snapshot of an ongoing exchange that predates human curiosity about the stars. In this view, our stellar system could be a hub within a galactic resource network, with countless routes and pathways regularly docking here, transporting materials, energy, or information into the vast darkness beyond. The secrets of these journeys might be encoded in the fiery plasma and magnetic activity of our star's corona, decipherable only by an intelligence sufficiently advanced to discern between natural phenomena and deliberate engineered processes. An intelligence capable of reading the subtle signatures in the dance of matter and energy that surrounds every star. Part 14. The conflict play, rescue, retrieval, or purge, unfolds behind the luminous curtain of our sun, in a theater where human telescopes cannot see and only imagination can script the drama. October of 2025 might mark the final act in a cosmic confrontation that has been quietly brewing since the first sightings of these visitors in our sky. Three scenarios emerge from pure speculation, each casting our mysterious visitors in roles that elevate them from passive explorers to active participants in a larger struggle, be it for control, information, or cosmic security. The rescue scenario presents a narrative of technological salvation, where Swan R2 does not arrive as an independent visitor but as a response, an emergency deployment aimed at aiding a distressed probe. In this interpretation, the interstellar object from beyond our system is not a healthy scout, but a damaged vessel. Its anomalous chemical signatures betraying signs of system failure rather than exotic composition. Its unusual signatures might reflect internal malfunctions or system breaches, hinting that what we see is not an intact explorer but a probe in distress, possibly in need of rescue or neutralization. In a plausible scenario where Swan R2 operates primarily as a sophisticated collection vessel rather than a rescue unit, its role would be to retrieve critical data or equipment from a probe that had fulfilled its mission and was no longer operational. The observed nickel emissions, devoid of the accompanying iron signatures typically seen in natural outgassing, might suggest hull breaches or component failures, damage that's causing the release of industrial materials into space as the craft struggles to sustain its basic functions. As Swan R2 emerges dramatically from behind the Sun during solar conjunction, this event takes on a new, more purposeful meaning. It signals an emergency deployment rather than a routine encounter. The craft's spectacular tail development could be interpreted as a concealed array of rescue or collection systems unfurling rapidly, masking the true nature of its operations, possibly deploying specialized equipment designed for precise data transfer or physical retrieval. During the critical phase of the solar encounter, when thermal stress and intense radiation could threaten to obliterate any remaining functioning systems, Swan R2's trajectory would need to be meticulously aligned with that of 3I Atlas. This alignment would be essential for a successful interception, particularly if the operation involves the subtle transfer of data or equipment. The craft might follow a carefully choreographed course, matching velocities and orbital paths with the interstellar probe, all while deploying collection mechanisms that appear to be natural cometary outgassing but are, in fact, sophisticated tools for asset recovery. This staged operation could involve several complex steps: physically gathering the smaller craft, perhaps by enveloping or ingesting it, an event that to our instruments might resemble a collision or fragmentation. However, rather than destruction, this process would signify a successful retrieval of intelligence, equipment, or data that the smaller probe had been sent to gather. The timing of this convergence, both objects approaching the Sun, would be deliberately chosen to optimize conditions for data transfer, minimizing the chance of detection by Earth-based observatories and reducing the risk of interference or observation during the critical moments of operation. Such a scenario aligns with the broader concept of staged, covert missions for interstellar intelligence gathering, where disposable reconnaissance probes are sent ahead of larger carrier vessels to collect information and return it securely. Given the enormous energy expenditure required for interstellar travel, it would be impractical to send smaller craft back to their origins. Instead, larger, more robust collector vehicles like Swan R2 would be designed to gather multiple completed missions over time, following trajectories that allow for eventual safe return to their base of operations. This interpretation also lends itself to darker possibilities. It could suggest a purge scenario, an ominous interpretation of the October convergence, where Swan R2 arrives not to assist or recover, but to erase evidence of the passage of 3I Atlas through our solar system. In this light, the mission might be clandestine, aimed at sanitizing data or remnants that could reveal the true nature or origin of these objects, effectively covering up any signs of non-natural activity and preventing the dissemination of potentially disruptive information. In essence, this scenario portrays Swan R2 as a covert, highly strategic asset, an interstellar data collector executing a staged, clandestine operation to retrieve, secure, and possibly hide evidence, all while minimizing detection. The timing, trajectory, and behavior of these objects could be meticulously planned as part of an intricate, long-term protocol for interstellar reconnaissance and information management, with the October encounter representing the culmination of a carefully orchestrated sequence designed for maximum secrecy and operational efficiency. In this conceptual framework, the interstellar visitor is envisioned not merely as a wandering celestial body, but as a sophisticated beacon or communication platform that has, for some reason, surpassed its intended operational limits. Such an object might have been actively transmitting signals back to its original controllers, revealing hints of artificial intelligence or technology, or perhaps inadvertently exposing its engineered nature through detectable electromagnetic signatures. These signatures, which could betray its true origins, might include unusual spectral emissions, anomalous radiation patterns, or other markers that stand out against the backdrop of natural cosmic phenomena. Enter Swan R2, transforming into what can be imagined as a covert cleanup crew, dispatched with the explicit purpose of erasing any tangible evidence of this supposed technological intrusion. Its mission would be to eliminate traces that might allow human observers, scientists and astronomers alike, to ultimately confirm the artificial provenance of these objects. This operation would involve more than just the physical destruction of the probe designated as 3I divided by Atlas. It would entail a systematic dispersal or disintegration of its remains in such a way that forensic analysis becomes impossible. Advanced disintegration technologies, perhaps utilizing energy-based systems or nanoscale molecular breakdowns, might reduce the probe to its fundamental atoms, scattering these particles so thoroughly that no residual structure or configuration remains discernible. The process would be meticulously timed, carefully calculated to coincide with moments when human observational capabilities are at their weakest. As both objects sink into the intense glare of the sun, their signals obscured and their visibility diminished. The timing of this sanitization would be orchestrated to occur precisely during the period when ground-based telescopes and space observatories are incapable of monitoring the event. This deliberate timing ensures that no direct evidence of the destruction or subsequent evidence disposal is captured by human instruments, effectively cloaking the operation from detection. Such a scenario compels us to reimagine the spectacular displays often observed in cometary activity, bright tails, expanding comas, and sudden outbursts, as possible camouflage for clandestine operations involving highly advanced, perhaps even extraterrestrial technology. These apparent phenomena might be masking energy weapons, matter disintegration systems, or exotic propulsion mechanisms that manipulate solar wind and magnetic fields. Technologies operating at the intersection of current human understanding of physics and engineering principles far beyond it. However, these dramatic interpretations face a fundamental challenge: the persistent reality of observational data, which until now shows no concrete signs of conflict, coordination, or artificial interference. Both objects continue along trajectories that are consistent with gravitational mechanics, following paths predicted by natural orbital dynamics. Spectroscopic analyses reveal emissions typical of sublimating ice and dust, signatures that align with natural cometary activity, without indications of anomalous accelerations or course corrections that would suggest active maneuvering or control. Moreover, no electromagnetic signals have been detected that would indicate artificial power sources or communication systems in operation. Our most promising potential witnesses during these critical phases are the spacecraft orbiting Mars. Positioned to observe the encounter on October the 3rd, These robotic explorers carry instruments primarily designed for planetary science rather than exotic phenomena detection. Nonetheless, they might capture subtle evidence of interactions that exceed natural explanations, such as unexpected emissions, anomalous tail behaviors, or other signatures hinting at artificial influence. The European Space Agency's coordinated efforts to monitor from Mars represent our best chance to maintain surveillance during periods when Earth-based telescopes are rendered blind by the sun's overwhelming glare. Yet the limitations of current Mars orbiters impose significant constraints. Their sensors and instruments optimized for planetary observation are not specifically calibrated to detect subtle or high-energy anomalies at these distances. As a result, only the most conspicuous deviations, large-scale or highly energetic phenomena, would stand out against the expected natural background. Consequently, any clandestine operation involving delicate energy manipulations or covert disintegration would likely go unnoticed, further complicating efforts to uncover potential artificial activity. In essence, this scenario urges us to accept that the universe's natural phenomena might be masking far more complex engineered processes, concealed behind the guise of spectacular cometary displays and cosmic fireworks, while remaining indistinguishable from natural activity within our current observational limits. Part 15. The October Silence. As the cosmic ballet unfolds, the communication between Earth and Mars faces an insurmountable obstacle, the fundamental delay inherent in interplanetary signals. The 12 to 24-minute lag in transmitting data means that any attempt at immediate intervention or response during a potential conflict or unexpected event will inevitably arrive too late, rendering real-time control impossible. We are left as silent witnesses, passive observers of whatever transpires in the vast expanse between our red neighbor and the distant unseen wanderer, an encounter that might be playing out just beyond our reach, in the shadowed realm of the sun's overwhelming glare. This inevitable silence, this void of direct influence, feeds into a deeply ingrained aspect of human psychology. Our minds are naturally inclined to interpret ambiguous phenomena through familiar narrative frameworks, stories of struggle, resolution, triumph, and defeat, stories that lend meaning to the chaos of the cosmos. It is a pattern-seeking instinct, a desire to find purpose in randomness, to assign intent where only chance might exist. These dramatic visions transform the silent, cold dance of celestial bodies into meaningful action, even when that action might be destructive rather than constructive. When the moment of clarity arrives, when our telescopes finally pierce the sun's fiery curtain and regain their focus on the cosmic visitors, will the universe reveal a familiar pattern? Will we find that the objects we tracked, those that vanished behind the sun, are still there, their orbits, compositions, and behaviors aligning with the models of natural cometary physics? Or will the universe surprise us with conflicts and resolutions that play out on scales so vast and complex that they challenge the very limits of human understanding? Could we be witnessing in the silent dark interactions and battles beyond our most imaginative theories, scenarios where intelligence operates on a level that defies our current capacity to perceive or comprehend? Part of the haunting beauty of this moment, the so-called October silence, is the gradual fading of our instruments one by one as the two visitors slip into the sun's overwhelming radiance. Observatory feeds flicker, then fade into darkness. Coronagraphs saturate with blinding light, obscuring all view of what once was. The greatest spectacle in our celestial neighborhood, these visitors from distant stars, disappears behind a curtain of hydrogen fire, leaving us with only memories, speculation, and the steady ticking of atomic clocks that mark the countdown to potential revelation. Across the globe, from government research facilities to university observatories, astronomers hold their collective breath, eyes fixed on the silent skies. Meanwhile, social media platforms buzz with a whirlwind of amateur theories, artistic interpretations, and wild conjectures. An explosion of human imagination filling the void where data once resided. The absence of concrete information becomes a fertile ground for every possibility that the human mind can conceive. In this enforced silence, all scenarios, natural or artificial, benign or hostile, appear equally plausible. Each interpretation carries the weight of potential truth, each a frame from the incomplete, unfinished film of our cosmic story. What will happen when at last the objects re-emerge from behind the sun? Will they return altered? Perhaps their colors shifted, their brightness faded or intensified, forever changed by their encounter with our star. Might one or both objects emerge dimmer than expected, or not at all, consumed or transformed by forces beyond our measurement? Could the debris left behind, such as a delicate ring of fragments, stand as silent witnesses to some cosmic transaction, a secret exchange conducted in privacy, hidden from our view? Or will nothing apparent change, and the only alteration be in our own hunger for meaning? Our relentless drive to find purpose amidst the dance of gravitational mechanics and the poetry of sublimating ice? The path forward remains rooted in patience, observation, and meticulous measurement. The story of these celestial visitors will only be written in the slow accumulation of data, each photon captured, each spectral line analyzed, each orbit refined. The upcoming weeks, especially as Swan R2's luminous tail reaches its peak, will offer amateur astronomers their most compelling chance to witness the comet's spectacular display. Its tail, sweeping majestically across evening skies, provides a visual testament to the ongoing cosmic drama, a reminder that, even in silence, the universe whispers its secrets to those willing to listen with patience and curiosity. As December approaches, our most advanced instruments are poised to resume their meticulous examination of the celestial visitor, once it emerges from behind the sun's luminous veil. If our current models remain accurate, this enigmatic object, often referred to as 3I divided by Atlas, will finally be visible again, allowing scientists to piece together its chemical signatures and trace its orbital path with renewed clarity. All existing evidence increasingly points toward a natural origin, rather than any extraordinary intervention. The convergence of two remarkable comets, destined to cross paths within the inner solar system, speaks more to the elegant mathematics of orbital mechanics than to any deliberate choreography orchestrated by intelligent design. Their synchronized approach appears to be a product of the universe's inherent order, a dance dictated by gravitational laws and the distribution of primordial matter, rather than a sign of cosmic puppeteering. The true scientific value of this moment does not lie in confirming our most extravagant hypotheses. Instead, it resides in the opportunity to deepen our understanding of how other star systems form, how pristine materials from the galaxy's distant outskirts are transported and preserved, and the complex processes that shape celestial bodies as they encounter the fierce radiation of our sun. Each observation, each spectral line studied enriches our knowledge of the universe's natural history, revealing the pathways through which cosmic objects evolve and interact. Yet amid the quiet between measurements, in the stillness that stretches between the vast data points, stories begin to take root. Human curiosity is innately pattern-seeking. We live in a universe sufficiently expansive to host both the predictable laws of physics and the tantalizing possibility of the extraordinary. This October silence serves as a silent canvas upon which we project our most profound questions about intelligence, purpose, and our place within the grand cosmic tapestry. If an ancient, perhaps artificial machine had established a rendezvous at our star, what would it discover in this tiny corner of space? Would it recognize a young planet teeming with a species just awakening to the vastness beyond, already broadcasting its existence through the electromagnetic chatter of civilization? Or would it uncover something far more unexpected, a complex symphony of hopes, fears, and uncertainties echoing across the eons, woven into the fabric of cosmic time? When December's light finally returns our visitors to view, and the instruments begin their quiet transmissions, reporting position, velocity, and spectral signatures, we will hold our answer. The question, echoing through 14 chapters of wonder and speculation: is it a comet, a fortress, or perhaps the reply to a message we never knew we sent? Until that moment, we remain in the October silence, cradled by the gravitational embrace of our sun, pondering what stories the darkness might be inscribing in languages we have yet to learn to read. The universe guards its secrets carefully, revealing them only to the patient. It rewards those who wait with the promise of revelation, whispering truths in the quiet moments between discovery. Good night.